Right. Mic testing, mic testing.
అది బాగాలేదు సార్. స్పీకర్ జాయిన్ అయ్యిందిగా యూఎస్ నుంచి. ఇద్దరు మీరు ఇక్కడ జాయిన్ అయ్యే వరకు సౌండ్ వస్తుంది. పక్క పక్కన ఉంటే సార్ ఓకేనా సార్? ఇప్పుడు ఇంకా కోవర్స్లో ఎవరెవరు ముగ్గురు
మేడం మన విఎస్ రెడ్డి జాయిన్
కాలేదా?
మన వినోదన్ మేడం కూడా జాయిన్
అవ్వలేదు.
సరే వీళ్ళు నలుగురు
ఉన్నారు సార్, ఇక్కడ చూసి చేయడమే సార్.
ఓకే, దీనిలో కనపడుతుంది కొంచెం వాటర్ పడుతుంది,
స్పీకర్ వచ్చేసి
కొంచెం అడతారు లోపల.
మేడం వెళ్ళారు కదా? ఓకే ఓకే, నో ప్రాబ్లం. మా సార్ తీసుకుని పిల్లలు మేడంతో పాటు వెళ్ళండి. మేడం తీసుకుంటాం తక్కువ తీసుకొని
ప్రెసిడెంట్ ఎవరు? సెషన్ ప్రెసిడెంట్ కన్వీనర్ మేడమా?
కన్వీనర్ మేడం, నేను
ప్రెసిడెంట్ ఆఫ్ ది సెక్షన్ ప్రిన్సిపల్ మేడం, వైస్ ప్రిన్సిపల్ మేడం పిలవండి. తర్వాత చీఫ్ గెస్ట్ తర్వాత కన్వీనర్ పిలవండి. తర్వాత
So good morning, ladies and gentlemen. So myself, Dr. Parvatalu Kalakunda, Assistant Professor of Physics, Organizing Secretary for the International Conference, Advances in Smart Nanomaterials. A respected patron, Sri Naveen Mittal sir, patron Soundarya Joseph madam, Rules Project Officer, guest of honor, Sri Dr. G. Yadagiri sir, Sri Dr. D.S. Rajendra Singh sir, Chairpersons, Principal sir Balabhaskar sir, Vice Principals Madam Dr. Aija Sultana madam, Dr. Viplav Datta sir, IQAC Coordinator Dr. J. Neeraja madam, Convener Dr. Naina Vinodini madam. So the importance of this conference, to bring the, important nanomaterial nanotechnology. So I invite today chair of the program, Srimati Dr. Aija Sultana madam. Please come on to the dais with a big claps. I also request today chief guest Dr. JD Dr. D.S. Rajendra Singh sir. Please come on to the dais, sir. Thank you, sir. So I also request IQSC coordinator Srimati Dr. J. Neeraja madam. Please come to the dais, madam. I also request convener of this conference, Dr. Naina Vinodini madam, in charge of Department of Physics. Please come on to the dais, madam. Now I handed over mic to the Dr. Naina Vinodini madam to proceed further.
Respected RJD sir, Dr. Rajendra Singh sir, ma'am, Vice Principal ma'am, Dr. Srimati Aija Sultana ma'am, IQSC Coordinator, Dr. J. Nirja ma'am, and dear students, good morning everyone. Let us begin the program with a joy because it is an academic festival we are celebrating in the City College. So on behalf of Department of Physics, City College, we welcome you all for this academic occasion. The order of the program is, we'll begin with the lighting of the lamp, prayer song, and the introduction of the topic by myself, and follows the few words from our chief guest, Rajendra Singh sir, Aija Sultana madam, and Nirja ma'am. Let us begin for we'll proceed for the lighting of the lamp, and we'll go. Thank you.
सुजलां सुफलां मलयज शीतलां शस्यश्यामलां मातरं वन्दे मातरं वन्दे पुलकितयामिनी पुल्लकुसुमिता द्रुमदरशोभिनी सुवासिनी सुमधुरभासिनी सुखदां वरदां मातरं वन्दे मातरं वन्दे मातरम्.
Please be seated. At the outset, I really thank Dr. Rajendra Singh sir for sparing so much time for us, and he has started in the early morning to spend some time academically with us. Thank you so much, sir. Let me take this opportunity to introduce the topic of the two-day conference. A very good morning to you all. This is Dr. Naina Vinodini, in charge, Department of Physics. On behalf of the principal, staff and students of City College, I deem it my pleasure to welcome our honorable guests and delegates for the two-day international conference, and the focus is on advances in smart nanomaterials. I stand before you all to give you a brief note on today's conference, but before I start, let me quote Bernard Marcus. The quotation is as follows: I am basically a dinosaur. I don't use email, but I do recognize the importance of science and the resulting possibilities. Let me introduce the topic. Nanoscience and nanotechnology have indeed advanced in such a fashion they are utilized in various applications. The properties and structure of nanomaterials differ significantly from their bulk materials. At nano range, the materials have multifunctionalities. Rather, they behave active, smart, and intelligent nanomaterials with higher performance level. Further, by using lower quantities of raw materials, reducing necessary maintenance operations, in turn saving energy resources and materials without polluting environment. The application of smart nanomaterials are synthesized nanomaterials which can apply in gene targeting, that is the desired babies, or to remove the ailments at gene level for their progress of life or healthy life. And the second is the drug delivery, magnetic drug delivery or drug delivery to the diseased parts of the body. Chips, everywhere the electronic chips are using in variety of applications. And not only chips, there are foldable chips also, both in chemical and biochemical assays, the nanosensors and nano composite. It is noteworthy that there is explosive scientific growth in the field of nanoscience and technology due to the introduction of new methods of nanomaterials in synthesis and advancement in the analytical techniques for the characterization and manipulation of material in the nanometer range. We have speakers from 5 different countries, sir. America, Germany, United Kingdom, New Zealand, and Australia. I can say that across the globe. And apart from the foreign countries, we also have the speakers from IIT Guwahati and IIT Hyderabad and the reputed the University of Hyderabad also. And they have done their research extensively in this particular field, and they are going to share their knowledge for us. So I request all the students to make use of this two-day conference and make benefit and get the interest towards the research. That's the very objective of the program, is to inculcate research aptitude in the students, because we have post-graduation also in our college, sir. So after they finish their post-graduation, we would like to join them. Many of them are interested to become scientists. So to join them as scientists, and we wish the progress, we wish all the best to our students. And I once again welcome you all to this two-day international conference, and I hope it will be a great success and insightful. Thank you one and all. Now I request Nirja ma'am to say a few words about this topic. And come like this.
Good morning to all. Respected Chief Guest, our Joint Director, Dr. Rajendra Singh Sir, President of the session, Vice Principal Ma'am, Aizad Sultana Garu, Convener of the two-day International Conference of Physics, Dr. Naina Vinodini Garu, and Organizing Secretary, Dr. Parvatalu Garu, and the team from Department of Physics, all the faculty members of Government City College, and all dear students. It is very happy to be a part as an organizing committee member of this conference, international conference, which is happening today and tomorrow, inviting so many delegates, as Naina Vinodini ma'am just now told that almost from all the continents, delegates are going to give their knowledge on this topic, advances in nanomaterials. I hope they also throw some environmental perspective on this, because when it is advancement, definitely it should also make a point of taking into the consideration of environment perspective. So I wish all the best to Physics Department, and I also wish the other departments to tap funds from RUSA, TSHE and other agencies, funding agencies, to organize such programs, which will definitely benefit the students and also the research abilities of our faculties. So coming into a degree college or an autonomous institution should not stop us gaining knowledge or doing research. And from this dais, I congratulate Dr. Parvatalu Garu, who got his chance to give his paper at some international conference in Italy, it seems. And he also got airfare from BC Welfare, and definitely he will also get that the remaining amount he will get from our college as per our research committee policy. And I wish more faculty from our college tap the funds from agencies and also from college. Thank you for giving me this opportunity, and all the best for this two-day program. Thank you, Vinodini ma'am.
Thank you, ma'am, for your nice words. Now I may request Aizad Sultana ma'am to say a few words about this.
Respected Joint Director Sir Dr. Rajendra Singh, and Head of the Department Physics Dr. Naina Vinodini Madam, IQAC Coordinator Dr. Neeraja Madam, and Organizing Secretary Dr. Parvatalu Sir, and my dear colleagues and students. So today the Department of Physics has inaugurated a two-day conference on nanotechnology, advances in smart nano materials. And this topic indeed is very interesting topic. As we know that human beings, right from the beginning of this universe, have been trying to develop themselves to move forward and forward, and they went on researching something for the betterment of their life. So nanotechnology is the most promising technology in this century, and many scholars they are of the opinion that the 21st century belongs to nanotechnology. So as the term suggests, nano, the term nano, it has come from the Greek word meaning very tiny, small. So as in every branch of knowledge, the Greeks' contribution is always there. So in the same way, the Greeks were first to think about nanotechnology. But we could not find any kind of literature available from the Greeks. But according to the available literature on nanotechnology, Romans were the first to use nanotechnology. In London Museum, a cup has been, it is there in London Museum, a cup which is the illustrating example of nanotechnology which is used during Roman period. So that cup, it shows that how nanoparticles were used in the making of that cup. And afterwards we see that in medieval period also there was use of nanotechnology, but those people, they did not know that it is a nanotechnology. So it is only in 1989 or 90 that the famous Nobel laureate physical or physics Nobel laureate Richard Feynman, madam, Richard Feynman, yeah. I think he is regarded as the father of nanotechnology. So in today's world, the importance of nanotechnology is growing at a rapid scale. And we see that nanotechnology can be used in this century, at least in the next half of the century, in every walk of human life. Actually, what is nanoparticles? Nanoparticles are very, very tiny particles. It has an external and internal structure dimension ranging from 10 to 100 nanoscale, and nanoscale is equal to 1/1000th of 1 centimeter. So it is such a tiny particle which cannot be seen by ordinary eye. So it should be seen by a very particular microscope. And this microscope, STM, it was, I think it was discovered or invented by one famous Nobel laureate only. I do not remember his name. So the nanotechnology, it is very progressive, and in the days to come, it will definitely help human beings. See, in all fields, and industries, commerce, foreign affairs, defense, forensic, everywhere, particularly for defense, there may come a time when a little tiny robots like mosquito will be produced and it will be utilized as spy cameras. And there will be very tiny robots which will be inserted in the body of human beings to see that whether any disease, a future disease will be there in a particular human being or not. And then and there itself that robot will cure, and thereby the span of life of human being will be very, very expanded, increased, and a day will come when human being will live for 200 to 300 years, as we have heard in stories in our childhood. There was a time when people used to live for 200 to 300 years. So in the same way, it will spread to every walk of human life. And I have read in one article that in production, in agriculture, in industries, it will be useful, and it will be very cost effective also. Everything will become cheaper. And even the clothes will be produced in such a manner that clothes will be dirt effective, dirt proof and waterproof also. So we need not wash our clothes. So a time will come that people will become, today only we are so lazy, and I don't know what will happen when all this, so actually today our life has become so easy, and it will going to be more easier. And there may be negative and positive effects of every technology, and God forbid it should not be taken in a negative manner, because people are there to take it for commercialization and privatization. If this technology goes for privatization and commercialization, then it will be misused. So it is depend upon the statesman, it is depend upon the rulers to see that this technology should be used for the benefit of human beings only, not in a negative sense. So thank you one and all for giving this opportunity. Thank you.
Thank you so much, ma'am. 2 days contents you have given in a nutshell. Now we are afraid to talk about physics in front of you because you have explained. I am telling you what all our topics you have covered. They are going to be discussed in detail in these 2 days. Thank you so much, ma'am, for your nice words. Now I may request RJD sir, Dr. Rajendra Singh sir, to say a few words. Thank you, sir.
Good morning. I am very happy to conducting a 2-day international conference on advances in smart nanomaterials. I am congratulating the principal, Dr. Balabhaskar Garu, the chairman of the seminar, and also the convener, Dr. K, the organizing secretary, Dr. K. Parvatalu, convener, Dr. Naina Vinodini, madam, and as well as co-conveners, Dr. Y. Vasudev Reddy and Dr. D. Chinni Krishna. I also congratulating the vice principal, Madam Ija Sultana, where she has given the nutshell, the picture about the today's seminar, and also congratulating the IQAC coordinator. Really, it is one of the very important topic, the current topic. The chief patron of this seminar is our beloved commissioner, Sri Naveen Mittalji, IAS, who is the moving spirit to conduct all the different types of the activities in the Telangana states of the various degree colleges. I am also, on behalf of our commissioner, on behalf of Commissioner Collegiate Education and the patron Dr. Soundarya Joseph, really all the staff members, organizing committee, those who are going to be involving actively in the conducting of the seminar. Globally, the participants are the main important resource persons, scientists, those they are going to be working. Various countries, they are also taking part in the seminar. Really, it is a great opportunity to the students to enlighten yourself, to know yourself, what are the important aspects which are going to be taking place. Because the nanotechnology is the very important topic, very important subject, where you are going to be seeing different types of the applications and future. The total almost all, everywhere we can find the nanotechnology. Without the application of the nanotechnology, we cannot see. Physics is the one of the very important subject, where we are going to be seeing the world in the cell phone, where we are going to be seeing the technology in the cell phone. Like all the different types of the innovations are going to be totally made. The one of the, besides of the fiber optics and as well as the superconductivity, the nanotechnology is the one of the very important topic, very important subject. Like you, the students, you are going to become a young scientists, you are going to be role models, and while attending such type of the seminars, you are going to be enlightened, and as well as you can easily involve actively in the research mode of, because naturally when we are going to be conducting on behalf of the Commissioner Collegiate Education the Jignasa projects, where our Commissioner sir is always giving top priority and as well as he is giving a scope to the students. If you have the scientific temper and as well as the technology and the scientific attitude, that will be come out when you are going to be actively involving in the preparing the project and as well as the presenting the project, and as well as you are going to be involving statewide, and cash awards are also going to be getting you, and these are all the things are all the so that it is a very important program for the students, especially why I am telling, because you are the scientists, future scientists in the national labs. You are the future professors in the important institutions. You are the, because that type of the attitude which will come out when you are going to be attending such type of the seminars, right? The nanotechnology is the one of the very important topic. Already I told you, everywhere you can find the nanotechnology. Once when we have seen the fiber optics applications, the total endoscopy and as well as the medical field has been totally drastically changed, and as well as we are going to be involving various important activities like which is having, basically I am from the botany, but I know little amount of the physics where the character of the total internal reflection. Here the nanotechnology is the subject you can find. It is one of the, because science, technology, engineering and as well as it is applied aspects of the mathematics and physics and all these subjects. The technology and as well as the science and technology is totally involving in it. Now here very important where the Vice Principal Madam, she told the important few applications of this nanotechnology, because in future generation we are going to be finding, we are going to be wearing the cloths with the nanoparticles which are made it, and they are dust proof, and as well as they are going to be totally, because nowadays we are going to be wasting different types of the aspects, antimicrobial types of the cloths are also going to be, we are going to be receiving a repellent type of the bacteria and as well as the virus and all these microbes. So such type of the particles are also going to be prepared. The nanotechnology is the one of the very important subject where we are going to be finding, where the market is going to be getting such type of the clothings. And here in medical field nowadays, because where the drug is required, where the target is required, how much amount of the quantity of the drug, that much amount of the quantity of drug we can supply with the nanotechnology. Here wasting of particles, wasting of the drug, wasting of the any substitute, that cannot be possible with the nanotechnology. So that nanotechnology is one of the very important aspects. Nowadays we are going to be finding different vehicles are there. The vehicle paintings, we are going to be using the shiny color type of the painting, that is only because of the possible with the nanotechnology. The new type of cars where we can see dust proof, and as well as just you can clean it in a properly, the shining will be continue remains because of the nanotechnology. That is the one of the very important type of the aspect. Several types of adhesives are in market because of the nanotechnology. New important adhesives which we are going to be finding. The colors are also going to be shining every even 10-20 years of the, once you will paint it, immediately the shining will be continue, and because of that is only because of the possible with the nanotechnology. Like all the different types of the coatings which we are going to be prepare, which we are going to be making, all the different types of the aspects. Like nowadays here several applications, nowadays the computers and as well as the accessories of the computer and as well as these important chips and important aspects which you are going to be using. When we can see the popular nanotechnological products, the titanium dioxide, silicon dioxide, these are well versed, which we are going to be seeing. The scratch proof eyeglasses which we are going to be using, that is only possible with the nanotechnology. Because when we are going to be, it is in market, we are going to be using the scratch proof eyeglasses and as well as the crack resistant paints. Even a paint cannot be, because almost all it is a resistant nature which will get it from the nanotechnology. The anti-graphite type of the coatings which we are going to be possible, like all the important aspects where we can find, and the important stainless replicants and as well as the fabrics and as well as ceramic, the important solar lights and solar cells, all these things are going to be because of the nanotechnology. If you are going to tell, there are several applications, there are several uses, because in future the nanotechnology is the one of the very important subject where it is having the broader scope. Like you people, you are the generation, the younger generation, you think it, and as well as the you give concentration towards the subjects which you are going to be upcoming subjects. The one of the upcoming subject is the nanotechnology. Okay, with this, because the foreign scientists, they are waiting from the various places, and I am very much thankful to you, sir, for taking part to involving in one of the important two-day national seminar, so that on my own behalf, I am extending thanks to you, and even the participants, those they are taking, even the students, those they are taking part to attend such type of the seminars. It is I am congratulating them also to attending such type of the important seminar which is conducted by the City College, because the City College is one of the very important potential college, historical college, and to conducting such type of the seminars is one of the it is because the other colleges also involved to conduct several types of the seminars to enlighten the students and take the important applied subjects. With this, I am once again thankful to the Principal Dr. Balabhaskar Garu, and as well as the organizing committee for giving me this opportunity to share few words before you. Thank you one and all.
Thank you so much, sir, for your nice words. And many are aware of nanoscience and nanotechnology. We are really surprised to listen Richmond Feynman. He's a famous physicist, actually. From a political science faculty member, it's really glad to know that she has taken some note from the Google. Thank you so much, and thank you so much very much, sir, for your remarks. Now I may, because our principal sir is not there, he's joining us online, and he'll give you the opening remarks as well as the session. He'll start the session of today's program. And Dr. K. Parvatalu sir, he's the organizing secretary, and I can say the oxygen of this two-day conference. And he'll host the session for the morning session. Now, shall I request Mr. Thomas? Good morning, sir. Yes, sir, please. Good morning, sir. Sir, call change, sir. అంటే నా వాయిస్ వినిపించట్లేదు. సార్ గుడ్ మార్నింగ్ సార్.
గుడ్ మార్నింగ్.
వచ్చిందా సార్? సార్ సార్ నో సార్ పిక్చర్ రావట్లేదు.
గుడ్ మార్నింగ్ నయన వినోదిని గారు.
సార్ గుడ్ మార్నింగ్ సార్.
గుడ్ మార్నింగ్ నయన వినోదిని గారు. గుడ్ మార్నింగ్.
సార్ వాయిస్ వినిపించట్లేదు. సార్ ఆర్ యు ఏబుల్ టు హియర్ మై వాయిస్? గుడ్ మార్నింగ్ సార్.
yes.
సార్ వాయిస్ రావట్లేదు.
Good morning. Please continue.
Sir, please check your audio, sir. You're not able to hear your voice.
No, my audio is right, correct. Hello. Unmute కావాలా? అయ్యాను అన్మ్యూట్ అయ్యే ఉన్నాను.
Both audio and video are not able to see. Not able to catch up.
ఏం చేయాలి ఇప్పుడు? లింక్ వెళ్ళాలా? వినిపిస్తూ ఉంది. Now it is okay, na?
Sir, good morning, sir. We are all waiting for your opening remarks. Now
Good morning, Amma. Good morning. So am I audible to all the... Am I audible?
Yes, sir. Please.
Am I audible?
Yes, sir.
Hello. Good morning to all. Welcome to the two-day international seminar on advances in smart nanomaterial. The faculty, students, and research scholars from all the parts of the globe. It is a privilege for me to invite you all to this two-day international seminar. First of all, I must thank wholeheartedly our Joint Director Sri Rajendra Singh Garu for accepting our invitation to grace this occasion. Sir, because of your love and affection only towards our City College, made you to present as a chief guest to this inaugural session and given a message, a wonderful message to all our students. Thank you very much, sir, for your blessings. I also invite Professor Dr. Gary Vanke, University of Alabama, USA, to this today international seminar on behalf of City College, Telangana State. I thank you for accepting our invitation and participating as a resource person in this international conference. Sir, here we are all eager to listen from you on the topic of advances in smart nanomaterials. I also thank Professor J. Suranarana Garu, Indian Institute of Technology, Hyderabad, Nafisa Begum from University of Tübingen, Germany, and also Dr. Pamu Garu from Indian Institute of Technology, Guwahati, for this two-day international seminar. Because of your love and affection towards nanomaterials, made you to agree our invitation. We are all very proud to have you, sir, all on this conference. Nanoscience and nanomaterial is one of the most important topics for all the researchers, as these materials are giving lots of applications in many fields of technology. The nano means, as our vice principal rightly said, we all know it is 1/1 billion part, such a very small and tiny in the scale. Taking the bulk matter into a scale of 1/1 billion level, most of the physical properties like mechanical, electrical, magnetic, dielectric, optical are changing drastically for a bigger scale, which only attracts most of the researchers to make use of these materials in the applications. Our Department of Physics has chosen very interesting topic of present times. The deliberations and discussions of these 2 days will certainly useful to the young researchers who are working in this field. The gigantic personalities in the field of nanomaterials are going to deliver their lectures on a very tiny matter. Certainly this will help the UG and PG students of our City College, as well the research scholars over the globe. I once again take this opportunity to thank our beloved Joint Director Rajendra Singh Garu for sparing his valuable time with us, for his presence, and all the resource persons who accepted our invitation to deliver their lectures. Wishing you all the best for successful and fruitful completion of this two-day seminar. Finally, I must also thank our Commissioner Collegiate Education, which is supporting, the RUSA is supporting the financially to organize this particular seminar. I once again congratulate our Department of Physics, Head Department of Physics, Naina Vinodini, who is the convener, acting as convener for this program, and organizing secretary, the Parvatalu, and co-conveners, Vasudev Reddy and Chini Krishna, for choosing such a beautiful, wonderful topic of the present times, and also taken the resource persons from the entire globe. This is a wonderful thing. The students are going to get more benefit out of this particular program. Thanks to the organizers for giving me this opportunity. Thank you, one and all. Thank you.
Thank you. Because Chini Krishna sir rightly said, in physics department we are not poor. Panchapandavulu. మీరు ధర్మరాజు మమ్మల్ని నడిపించేవాళ్ళు సార్ అక్కడ eyes cataract surgery valla he could not participate in that. Thank you, sir. Thank you very much. Now I request Dr. K. Parvatalu, sir, to give a brief introduction about today's first speaker. And I also request our students to join online, because right from morning 10 o'clock to evening 4 o'clock, you can join anytime for all the lectures. We have displayed the program schedule in our department as well as near the principal room. Please go through it, and I request and encourage you all to join the online. Okay? Thank you. Thank you so much, sir. Over to Parvatalu, sir.
Thank you, Dr. Nayana Vinodini madam. So I'll begin session with a great quotation is given by scientist Einstein. Imagination is more important than the knowledge. Knowledge is limited, whereas imagination embraces the entire world. So coming to the today's session, first speaker from United States of America. Good morning, ladies and gentlemen. Today we are pleased to welcome very special invited speaker, Professor Gary Mankey from Department of Physics, University of Alabama, USA. Great welcome, sir. It's a great pleasure for me to introduce our speaker, Professor Gary, who is going to talk about, yes, please, big claps. So he's going to talk about probing nanoscale magnetic structure with a photon, light, neutron, and electron. He's an eminent faculty in the field of material properties, magnetic material, and nanostructures. He works with a team in National Laboratory, Oak Ridge National Laboratory, USA. The scattering result shows spin ordering behavior in anti-ferromagnetic film, spin structure, magnetic structure of superlattice will be presented. He completed his PhD from Pennsylvania State University in 1992. He was also a postdoctoral scholar in Pennsylvania State University, Louisiana State University. He joined as a faculty at University of Alabama in 1996. He received many awards from Oak Ridge National Laboratory, Faculty Fellowship. He also received National Science Foundation Award, Max Planck Institute of Plasma Physics, Germany. He also participated guest scientist in Lawrence National Laboratory. He published more than 300 international publications, which is really, sir, we are so honored to be here. Such a great, professor. He has been reviewer and editorial board member for many, many international journals. Today, he will share about probing nanoscale magnetic structure with light, neutron, and electron diffraction, which is going to be very, very exciting for us, sir. With that, I ask you all, give full attention to Professor Gary Mankey talk. The rights and privileges.
My slide. Can you see this slide or not? Hold on. Hello? Can you see the slide?
Professor, can I share your slide?
Yes, please share.
Thank you. Sure.
Slide with the green there. Share. There we go. That's better. So that's the title of my talk. Photons, neutrons, and electrons. And there we go. The property that we use photons and neutrons and electrons are, each of them has a size associated with them. And that's the wavelength of the photon, neutron, and electron. And this has to do with what the first speaker talked about, nanoscale. You cannot see a nanoscale object with visible photons. because a visible photon has a wavelength of about 5,000 angstroms, and a nanostructure is of the order of 1,000 angstroms. So it's 100 angstroms or nan. Visible light is 500. I'm sorry, I use the angstrom because I'm old. Angstrom is 1/10 of a nanometer. The size of an atom is 2 angstroms or 0.2 nanometers. The size of a photon is 500 nanometers. And so you cannot use visible photons to measure something as small as a nanometer. So what do? We use X-rays. X-rays have smaller wavelengths. Neutrons also have smaller wavelengths, and you can make an electron microscope that also has a smaller wavelength. These probes that have smaller wavelengths are then what's needed to see things on the nanoscale. My research focused on this, magnetic data storage. So this is the world's first hard drive. As you can see here in this picture here, the hard drive is as big as a room. And it only stored 5 megabytes of information in it. And it's only 2 years older than I am. So throughout my life, I saw all this, I witnessed all of this technology being developed. When I went to college, we had one of these devices in our school that had this stack of 12-inch diameter platters. There's many of them now. I don't know. There's something like 32 platters this big, and it only stored 5 megabytes of information on it. Of course, you know that's a small amount of information by today's standards. What do we have today? Well, this is sort of an outdated, but this is a hard drive that used to go in a cell phone. It has 4 gigabytes. That's megabytes. This is 1,000 times more information. And the reason that it has more information on it is the bits are now much smaller. They're nanoscale bits. The width of a bit giant magnetoresistor. What giant is because the resistance, the electrical resistance of the reader changes by almost an order of magnitude when a magnetic bit flies underneath it at a high speed because the disk is spinning very quickly, and that gives you a signal here. And that device there was invented in 1988. The giant magnetoresistive effect was discovered in 1988, and it resulted in a Nobel Prize being awarded in 2007 to Albert Fert and Peter Grunberg. So this is an example of something that was only invented. It was invented 10 years before it became a component in a consumer device. So here's the track. This is what's known as the Kreider plot. It's named after a researcher at Seagate, Dr. Kreider, and he made this plot here of the density of bits on a disk in megabits per square inch versus time, and you can see that it follows an exponential increase. So here we are today, we have something like a terabit per square inch of information on a disk, where before it used to be the first hard drive has a kilobit per square inch, kilo to tera. So that's 10 to the 3 all the way up to 10 to the 12. This curve had changed by 9 orders of magnitude, or it's the same number used in, it's 9 is giga, but 9 orders of magnitude smaller than a meter is a nanometer. So that gives you an idea of how much this product has improved over the course of my career. And this is already outdated, 2005. There's the application. All of you probably know about playing these games. That's what it enabled, these high resolution graphics and things to exist now, because we have such a magnificent amount of storage. So this is what we've been doing for all these years. In 1965, this is Time magazine. 1965, they thought the computer was going to rule the world. Does it? You think the computer has made a lot of wonderful things possible? Yes, it has. 2005, we had the Apple, and this is the what is it? The music player. That has a little tiny hard drive in it. 2013, can Google solve death? Where are we now? Oh, this is me, and this is one of my former graduate students. They're now digging for treasure. I showed them where to dig initially. And this is the key words. Motivation and perseverance are necessary to succeed. So that's the pep talk. Now let's get into the science. Oh, we talked about Feynman. How about Schrodinger? I said that you need to know quantum mechanics. This is the famous Schrodinger's cat. It has a wave function associated with it, and you don't know whether or not the cat is dead or alive until you measure the state of the cat. That's the basic principle of quantum mechanics. Quantum mechanics is a probability function. So what property? So these devices all include very complex materials. Inside here is a ferromagnet that's very soft. There's an anti-ferromagnet in there. There's also special materials in the right head that have a high magnetic permeability, and they can be switched very fast. The disk has a problem associated with it. In order to make the bits on the disk stable, you have to have a large value of K times V divided by KT. KT is the Boltzmann thermal energy. At room temperature, KT is about 25 milli-electron volts. KV is the magnetic anisotropy constant times the volume of the bit. So as you make the bit smaller and smaller, you must increase the anisotropy, the magnetic anisotropy of the material. So there are a number of materials problems here that need to be solved in order to make this curve advance further into the future. Ultimately, you'll be at the limit where the bit is the size of an atom, and you can't make it smaller than an atom. So that's the ultimate limit of this. Then we have to apply different ways. For example, you can go into quantum computing then, and in that case, you take an advantage of the fact that there are more, that a quantum mechanical system has more possibilities than simply a magnetic bit is either pointing to the north or pointing to the south. So there's only 2 states in a bit there. If you take advantage of a quantum mechanical process, you'll have more than 2 states, and you can expand the capacity of the device that way. So what do? I make these samples. I started by making very thin films. And this put me in a unique position because there are many scientists throughout all over the country here that want to examine my samples with their newest and greatest experimental measurement techniques. So I had the opportunity to use X-rays and neutrons to measure my samples. Typically, you didn't think of using neutrons to measure small things because neutrons scatter very weakly from a material. X-rays, on the other hand, they also are highly penetrating. So you have to use special sources that have extremely high flux and special detectors that have extremely high sensitivities to measure the interaction of these X-rays and neutrons with your small samples. We also do tricks like reflectometry. You can use X-rays and neutrons to reflect from a surface that has layers, like the coatings on the anti-scratch coating on a pair of glasses, for example, and other things, anti-reflective coatings on glass. We use different kinds of substrates, and we're primarily interested in metal films. You can also use transmission electron microscopy, and those instruments are available at national laboratory facilities. And this is also another technique that can be used, scanning electron microscopy with polarization analysis. In that case, the electrons, the spin orientation of the electrons can be used to measure magnetic domain structures. And I have one example of that. So here are the probes, X-rays. The wavelength in angstroms is equal to 12 divided by the energy in keV. Of course, you know, there's some fundamental physical constants, but this is how I remember it now. If you want to know if you have an energy that's in the order of electron volts, the way that I measure that, I remember that formula quickly is I use 1, 2, 3, 4, 5 divided by the energy in electron volts. So a 12,000 angstrom photon has 1 electron volt energy, and that's a small amount of energy. That's smaller than the binding energy of a electron to an atom or a solid. The binding energy of an electron to a solid is of the order of 5 to 10 electron volts. That's the reason that visible light also doesn't ionize materials. An X-ray, though, will ionize material, and it can be harmful as well. So we have to use proper shielding and engineering controls to prevent getting exposed to this ionizing radiation. You can control the polarization of X-rays and give them helicity. That allows you to probe magnetic structures. If the X-rays are left or right polarized, or right circularly polarized, then they have a spin associated with them, and you can use that to probe the spin on the electrons in the solid that you're looking at. And they also have no charge. A neutron, also no charge. Its wavelength is different. 0.28 angstroms divided by the square root of the energy. We use thermal neutrons that have energies, and those neutrons then have wavelengths of the order of angstroms or tenths of nanometers. They have spin on them, and we can control the spin of neutrons using spin filters and spin mirrors. So we can probe magnetic properties by looking at the spin scattering of the neutrons. And they also have no charge, but they're highly penetrating. So a 1 angstrom neutron has a wavelength has an energy of 78 millielectron volts. Now, earlier I said that KT at room temperature is what? It's 25. So this corresponds to a temperature of about 3 times room temperature. 3 times 300 is 900 kelvins. It's still considered to be cold compared to electron. We go to electrons. Electrons have a wavelength in angstrom of 12 divided by the square root of the energy in electron volts. So a 144 electron has a wavelength of 1 angstrom. Electrons can also be spin polarized. I've worked with devices that have both spin detectors based on the Mott effect, and they also have charge. So electrons at low energies don't probe very deeply into the solid. They only measure the top few layers. We use the wavelengths then to perform crystal diffraction. You have an incident X-ray or an incident photon, a diffracted beam. You rotate the crystal according to its crystallographic directions with respect to the incident and diffracted beams. And you have a diffraction experiment where there's initial K vector, and you measure you see a peak when the difference between the incident K vector of the X-ray and the exiting K vector is equal to 1 of the reciprocal lattice vectors of the solid. So this arrangement of dots here is the reciprocal lattice of a crystal. That's a standard solid state physics description. Here's the device that we use. It's called a Philips Expert X-ray diffractometer. You have an X-ray tube that emits X-rays of wavelength 1.542 angstroms. It interacts with your sample, and you move this detector around. You change the angle theta and 2 theta until the Bragg condition is satisfied. And when the Bragg condition is satisfied, you see a peak. So this is a silicon 100 wafer. The X-ray diffraction of that, taken by one of my students, Junchi Wu. And you can see, why are there 2 peaks? Well, silicon, the X-ray source is a copper cathode, and it emits radiation at 2 different wavelengths, 1.5406 and 1.5444 angstroms. And this is the 2p 1/2 and the 2p 3/2 transitions. So you can see the 2 different transitions due to the X-rays. Then when the Bragg condition is satisfied, you see a peak. There's 6 p electrons. 2 of them are involved in, 4 of them are involved in this transition, and 2 involved in this transition. So if you integrate the areas of these peaks, this one is 2 times larger than that. So when we typically align our system using a silicon crystal, and we see this at this is 2 theta plotted on the x-axis, 69 point, look at that, that's 69.2, that's 69.1, 69.14 is where the major peak is. You can look this up in the Center for X-ray Optics data book, X-ray data books, the principal X-ray emission energies that are used to get these wavelengths. And I might point out that my friend, what's his name? Jeffrey Courtwright, one of the authors, he missed a decimal point in the formula for converting electron volts into angstroms there. It's at the top of the page. So what do we look at? Why do we need diffraction? Well, this is silicon is boring. That's what you start out with. what we do is we put films on top of silicon. And this the film atoms. These are different ways they can arrange on the surface, either commensurately, pseudomorphically, incommensurately, and you use X-ray diffraction then to determine the relationship of the peaks due to this crystal to the peaks of the crystal below it. So these are epitaxial films, and there's the reference for that. This is 2017. I started doing this process here in 1986. So, but I like this diagram better, so I borrowed it from Lin Chen. So here are some examples of things that we've looked at. So in 1991, we experimented and found here, we plot the diffusion coefficients of surface diffusion and bulk diffusion and found that there's an optimal growth window in temperature relative to the melting point of the material that you're depositing, where you get a smooth film with a good crystal structure. So the growth of the crystal depends on diffusion. If you grow the film at too high of a temperature, though, the bulk diffusion, there's an onset of bulk diffusion, and the film dissolves into the substrate below it. So you have to be below the temperature where you get significant bulk diffusion, and above the temperature where the film atoms don't move around to make a smooth film. So this is an example of a multi-layer of samples, of a sample here. You can see this is transmission electron microscopy. You can see bright and dark bands, and that represents those bright and dark bands correspond to different materials that were deposited in the system. We've looked at things like films. This is a process called angle resolved photoemission, and you can map out the spin-dependent energy bands in the solid using this technique. And this technique measures in reciprocal space. This also measures, this is a low energy electron diffraction where we're looking at a crystal that has 6-fold symmetry. Those are electron diffraction spots. And that's also a reciprocal space technique. So you have to learn the principles that are used to convert from real space to reciprocal space. The mathematics of that is all well defined. When we make a film on top of a substrate, you have to measure the orientation of the film with respect to the substrate, and this is done using X-ray diffraction. And that's my co-author's name that did this. He made this film of iron, rhodium, palladium. This is a material that can be used in all parts of the sensor, and it's on top of a magnesium oxide substrate. These materials, iron, rhodium, and iron, platinum, and iron, palladium, all have ferromagnetic and anti-ferromagnetic phases. If you look at the high angle X-ray diffraction pattern of films, what's this? 10 nanometers, iron 50, platinum 45, rhodium 5, and then 20, iron 50, platinum 25, rhodium 25. And this is 8 repeats. So this is the real space representation of that film structure. And this is what you see in reciprocal space. You see satellite peaks around a normal diffraction peak, and that tells you what the periodicity is from bright band to bright band. I should point out that the X-ray diffraction experiment is non-destructive, while this sample here, this is transmission electron diffraction, and that is a destructive technique. You have to destroy your sample to measure that. You have to cut a small piece out and and polish it down to very thin so that you can, so that it's thin enough that the electrons can penetrate it. And this is another layered structure that we have in town. It's called carrot cake. It's very good. That's icing between layers of cake. Another thing that you can have when you measure X-ray diffraction is you can see oscillations in the X-ray intensity as you change the angle of the detector. And that tells you again that you have a very smooth film. And this is a film of rhodium. Oh, I don't know how thick it is. I'd say it's probably about 25 nanometers thick, but it shows that it's smooth over large distances, 1,000 angstroms, so 100 nanometer terraces. This picture here of epitaxy here that I showed here, this does not occur over very large distances normally. Normally you get patches of good growth and patches of bad growth. And those patches can be as large as 100 to 1,000 nanometers. And because we're making nano devices out of this, then when you process it, your device, you'll have basically this situation occur over the area of a device. In the hard drives, they are not the bits are not epitaxial films, but polycrystalline material, and the grain size is normally of the order of 5 to 10 nanometers. So here's another example. We made a film of iron platinum, and it's very good crystallinity, and it's also ordered, an ordered alloy. And you can use X-rays then to measure the order parameter of the alloy, or how well the iron and the platinum are arranged at specific positions in the lattice. And we'll go into the theory of that later. So you can order the iron and the platinum. And if this material is disordered, it's a ferromagnet. It has areas, it magnetizes in a specific direction, and it's ferromagnetic. It has a net magnetic moment at room temperature. If you order it chemically, then it becomes an antiferromagnet. An antiferromagnet has spins on the electrons of the iron. The platinum is only weakly magnetic, but the spins on the iron are arranged so that all of the moments add up to 0. That's an antiferromagnetic material. And we made these films of iron platinum 3. And we found that there are 2 different types of spin ordering. You see in this diagram, part A, the alternating planes along the 1/2, 1/2, 0 direction have alternating magnetic moments. So the atoms on this corner and this corner of the cube, these corners of the cube are pointing up, and the other corners are pointing down. This is another type of spin arrangement where the atoms on the 2 faces, alternating faces of the cube, go up. The spins on the iron atoms are either up or down. So this is 25% iron and 75% platinum. The irons have the spin on them, the platinum not. If you add up all the atoms in this unit cell, you'll find out there's a quarter. There's 3 platinum atoms on the faces here, shown without a spin on them, to every 1 iron atom that has a spin on it. Now, this graph here, which is from this paper here in 2001, was the first determination of antiferromagnetic order in a thin film. Previously, this technique has only been used in bulk crystals. And Brockhaus and Scholl were awarded the Nobel Prize for determining that neutron diffraction can be used to determine antiferromagnetic ordering in crystals. And they proved the long-standing theory of Louis Néel about the existence of antiferromagnetism in solids. And he also, so there's 2 Nobel Prizes here in that data there that we relied on these guys to guide us through this. And then we were able to measure. Look, this film is a little bit on the thick side though, 300 nanometers. It's on the outer limit of what you would call nanoscale material. We have since increased the sensitivity of this technique, and we can measure films as thin as 50 nanometers with this technique today. Where do you do it? You have to go to the high flux isotope reactor in Oak Ridge National Lab. And this is an old diagram. It has since been upgraded. But we made those measurements here at the HB1 axis, HB1 Ames Lab triple axis spectrometer with fixed incident energy. These are 2.2 angstrom neutrons. You have a fixed incident energy and a fixed wavelength of the neutrons. And here's how it works. You have a neutron source in the middle. There's water surrounding it. The neutrons produced in the nuclear reactor are have very high energy. As they travel through the water, they become moderated and they lose energy and become thermalized with the water, and they come out with a Maxwell-Boltzmann distribution of energies that's peaked at about 400 degrees Kelvin, I believe is what the peak is there. And we filter then the electrons using a graphite monochromator. So this first unit here is graphite. You put your sample there. Then you have another piece of graphite that filters the neutrons that are scattered from your sample. So you're only looking at the particular energy that is elastically scattered from the sample. A diffraction process, the particles do not lose energy when they diffract from the crystal. But neutrons can lose energies to excitations, magnetic and thermal excitations known as phonons. So you can actually look at the energy loss of the scattered neutrons then and measure them at your detector. And each element of those, each of the elements here, your monochromator, your sample, and your analyzer satisfies Bragg's law if you're looking at elastically scattered electrons. So let's take a look at what we mean by reciprocal space and how that is utilized to measure antiferromagnetism in solids. First of all, we're only going to look at a crystal in one dimension. So these green dots represent your scatterers. The X-ray form factor has this form here. It's a function of the electron density as a function of R. And Q is the Q vector of the incident beam. And from this, you get a peak whenever 2D sine theta is equal to n times some number times the wavelength of the radiation. So in this example, we have 3 different kinds of substrate. You know what Al2O3 is? It's sapphire. We use sapphire crystals because they're they can be made very flat. And the flatness of these substrates is useful. Also, you can heat sapphire to 1200 degrees C to deposit your film. So you can make very well-ordered films by depositing on hot sapphire. So this is rhodium that's deposited on sapphire at, I think here the growth temperature is around about 800 degrees C. There are different faces of sapphire, 112 bar O, 0001, and 101 bar O. These are different principal faces of sapphire called M, C, and A. And as you can see, when you put the rhodium film on this one, there's no peaks associated with the rhodium. On C sapphire, you get a little peak here to the left of the sapphire peak and a little peak there. And when you use 112 bar O, you still get rhodium 111 peak. It's a particular, rhodium is face-centered cubic, and the 111 X-ray diffraction peak is allowed because H, K, and L are all even, are all odd. In a face-centered cubic system, you see a diffraction peak when H, K, and L are all even, or all odd. So those are the two diffraction peaks. So this tells us that we have epitaxy, or does it? No, it says that we have a good texture of the film. Now what happens? So the rhodium is a pure metal. All the atoms here are green because they're rhodium. How about when we go to iron and platinum? An equal number of iron atoms to platinum atoms. So if the film is ordered chemically, then you see alternating red and green atoms, and now you have two periodicities, one at D and one at 2D, where D is the lattice spacing of the atoms. To get from one iron atom to the next, you have to go two lattice spacings. That results in an additional X-ray diffraction peak. This is the 002 peak. It's face-centered cubic. What did I say? The peaks had to be all even. The H, K, and L have to be all even or all odd. Here they're all even. This is allowed. But there's a forbidden peak here, 001. That peak occurs or shows up because there is an alternating row here in the form factor. There's a row 1 and a row 2 that gives you an additional periodicity, and that gives you then an additional peak. This is reciprocal space, remember? In real space, the periodicity is 2D. In reciprocal space, you have 1 over 2D. So there will be twice as many peaks for a crystal that's ordered this way. So here we're probing the nanoscale magnetic order as a function of growth temperature here. Here, this film here is grown at 300 degrees C. 400, you start to see that ordering peak emerge. 480 C is getting larger, 560 even more, and then 720, we see a fully ordered sample. And this is one of the essential factors that you need to see antiferromagnetism in the alloys that have antiferromagnetic order when they're ordered. Iron platinum, though, is ferromagnet when it's a good ferromagnet when it's ordered. The reason that we're interested in this material is for the media that the little bits are written on has to have a high magnetic anisotropy, and the magnetic anisotropy is larger when you have well-ordered film, chemical order in the film. So this film here has the highest magnetic anisotropy of all the ones in that set. Now what's happened? Oh, now we have a different thing happening here. When we add a little bit of rhodium you get a periodicity of 4D now. So this is another neutron diffraction experiment where we have an additional periodicity. Oh, this is antiferromagnetism on top of chemical ordering. So the iron atoms are here, here, oh no, blue atom, red, oh, so I had to make, oh, that doesn't show up as blue. I'm sorry, I didn't notice that. So the light green must be, oh yeah, the light green must be the non-magnetic atom. And the dark green is the spin down iron atom, and red is the spin up iron atom. So in order to go from a spin down iron atom to the next spin down iron atom, you have to go 4 lattice spacings. So this gives you, in addition to the 001 peak, another one at 001 half. You see a half order peak. And this is what Brockhaus and Scholl did to show the existence of antiferromagnetism. They did a neutron diffraction experiment, showed that there was half order diffraction peaks, and that proved that there was a magnetic periodicity in addition to the chemical periodicity. This experiment was done by my friends, and I provided a sample for my friends in Germany, and they went to the neutron source in Switzerland, I believe it was. Oh, and they made measurements in fields as high as 12 Teslas. So you're not only doing a neutron diffraction experiment here, you're applying very high magnetic fields. And also you have a temperature range of 100 to 300 degrees Kelvin. So it's a very advanced experiment there. It was done by my friends in Germany. And oh, this is ILL, the Institute for Laue-Langevin in, where's that? That's in France. Now there's another possibility, even more. You can make a material that has a helical magnetic order, and there the magnetic vector on the atom rotates in a plane 60 degrees from each atom to the next. So these different color atoms here represent different rotation angles of the spin vector on the electrons. So black is 0, red 60, orange 120, yellow 180, green 240, blue 300. And to get from a red atom to the next red atom, you have to go 6 lattice constants. And this particular experiment here involved a dysprosium crystal at low temperature. And we see a satellite of the diffraction peak that's equal to 1/6 of the distance between 2 diffraction peaks. And there's one on both on the negative and the positive side. So we do this measurement as a function of temperature and magnetic field, and we probe all kinds of different chiral and helical magnetic structures in the material. So, yeah. So how you control magnetic anisotropy with ordering. There's another material, even more interesting. This material here, iron, rhodium, palladium, is an antiferromagnet at low temperature, and it undergoes a first order magnetic transition to become a ferromagnet at high temperature. And that's highly dependent on the order parameter as well. This is what's known as a metamagnetic material. And this has applications in the hard drive industry as well. So these are the properties of neutrons. How are we doing on time? Are we doing fine? Oh, yes, we've got lots of time. Yeah. This is from the spallation neutron source page. We're going to do I'm going to show examples of another experiment. Called neutron reflectivity. Up until now, we've only been looking at the arrangement of atoms on a crystal and the arrangement of spins on those atoms, if they're magnetic atoms. Now we're going to look at films and look at the arrangement of spins within the film structures. Oh, this is another diffraction experiment. This one here was very puzzling, where we have iron, platinum, and rhodium, and we see this curious peak, 1/2, 1/2, 3/2. We thought we discovered a new kind of magnetic order. But if you make a model of those spin arrangements for different kinds for different orientations, where you have these models have different colored atoms. Red and green have up spins, and blue and yellow have down spins. You can see that if you rotate this crystal here with 1/2, 1/2, 3/2 order at the right angle, it will look equivalent to the one with the 1/2, 1/2, 1/2 order. So this was a puzzle that needed to be solved. It's just an equivalent, two equivalent diffraction events that probe the same spin ordering in the crystal. I don't know why I put that in there. Oh, it was a special case. So now what? Now we can do another thing. Inelastic neutron scattering. And this is quantum confinement of spin waves. Theoretical colleague of mine, Randy Fishman, predicted that if you made a superlattice of dysprosium and yttrium, you would get quantization of neutron diffraction. The scattering is very, very weak. So this data here isn't taken from a single sample. We made a dozen samples, as many as we could put into the cryostat, and stacked them all together. We made it as thick as we could make it, as many repeats as we could make it without destroying the epitaxy. And we put as many samples as we could in the diffractometer and still be able to cool them. And the signal was still too weak to measure. So this is an experiment that can be possibly performed in the future even further. And there is a spallation neutron source that's currently being built in Sweden, Lund, Sweden, that will be able to make this measurement. They'll be able to measure quantization of spin waves and learn more about the quantum mechanical properties of spin waves in the future. So we have one other topic to follow, to cover, and that's reflectivity. This is a thin film of water on top of some mirror surface, and it's being illuminated with white light, and you can see there are bands of different colors of light being reflected at this particular angle where this was measured. And that property of wavelength selection, where the blue light reflects strongly here and not so strongly there, can be used to measure the thickness of the film or the structure beneath the surface of the film. The first thing to note is there's some critical angle. Now, in this example, this is classical physics experiment. You're looking at light being refracted at the surface of water when the index of refraction of water is greater than the index of refraction of air. Then there's a critical angle where the refracted ray refracts at 90 degrees. So this is high index into low index. There's some critical angle where the light doesn't is refracted at a 90-degree angle. And it's reflected internally. There's another property of light that you have the Bragg equation that's satisfied here. There are particular angles where the reflected light is equal to, the path difference is equal to an integral number of wavelengths. Depending on the phase shift of this interface, you have the Bragg condition, or a maximum intensity at particular angles. Now what happens when you go to X-rays? Your X-ray beam starts out in air. How on earth can it be to undergo total external reflection? Air has an index of refraction of 1. Look at this. For X-rays and neutrons, the index of refraction is given by n is equal to 1 minus this number here. So it's smaller than 1. How is that possible? That's a question for your students there. How can the index of refraction be less than 1? And the reason is it represents the phase velocity of the light and not the actual speed of the photon. So ponder that. So the index of refraction depends on the wavelength and what's called the scattering length density of the material. And you can get these scattering length densities from a website, knowing the density of the material. This is iridium, and the source. This will tell you what the wavelength of the source is. And you look this up, it gives you a number, 10 to the minus 6 angstrom squared, and you find out that there's a critical angle of 0.4 degrees for copper and 1.5 angstroms wavelengths X-rays. That's just an example that I looked up. But this is X-ray reflectivity from a iridium surface. And you can see the critical angle is, for all intents and purposes, where the intensity, the reflected intensity drops by a factor of 2. So we get 0.625 degrees, and you look it up on this site here, calculate the, find out what the density is, the wavelength of the light, and you get 0.595 degrees. So it has an uncertainty. It's pretty close to the uncertainty in the measurement. So you can tell what material you have by looking at the critical angle of reflection. For less dense materials, that critical angle moves out, and more dense it moves in general. The X-ray scattering length density gets smaller for higher Z materials. So that's another fact. Let's look at the other thing. You can see oscillations due to the reflection of the two waves reflecting from the top of the film and the bottom of the film. This is called X-ray reflectivity. And you see these oscillations. Notice this is on a logarithmic scale, so the intensity gets smaller very rapidly. You can solve that problem of low intensity just by increasing the dwell time and the measurements at larger angles. You can plot those angles of the maximum versus their index and determine what the thickness of the film here is, knowing the wavelength of the radiation. So we have copper K alpha 1.542 angstroms. We make this plot, and from the slope, we can then determine the thickness of the film. And we get 120 angstroms, or 12. This is a 12 nanometer film. So this is truly a nano scale measuring technique. We're measuring a 12 nanometer, the thickness of a 12 nanometer film. And the thickness of these films is important for determining the properties. If they're magnetic, the films, magnetic properties depend on thickness. If it's, this is a iridium film, the resistivity of the film would be a sensitive film. The resistance of the film, not the resistivity. Resistance of the film will be a sensitive function of that thickness as well. So up until now, we got this angle 2 theta here that we're plotting. It's more proper to plot the reflectivity versus scattering vector. And the scattering vector is calculated as 4 pi over lambda times sine of theta. This gives you the scattering vector in inverse angstroms or inverse nanometers, depending on what you use for lambda. And then you can use this data fitting program called Parrot. It's a Windows program developed to fit this data, to then fit your data. So this is a similar set of data. The data is, it's the same set of data as the green dots. We put in things like the scattering length density and the wavelength of the radiation, what the substrate is, and fit it. And that then gives you a plot of scattering length density versus depth. And again, you can see that we start out at 0. We're at about 130 angstroms, or 13 nanometers thick. Oh, here you are, 130 angstroms. And this technique of fitting it also gives you another parameter, which is the roughness of the film. And you can see that the interface here between the film and air has only 0.5 angstroms of roughness, or 0.05 nanometers. And the interface between the substrate and the film has 1.8 angstroms of roughness, or 0.18 nanometers. So it's very, very smooth. Now in devices, what you want to do is layer these materials on top of one another. And you get a second kind of an oscillation called a Bragg peak. That's due to the periodicity of the materials that you're selecting to deposit. So here in this film in the bottom, you can see both thickness oscillations, but there are some enhanced peaks at particular angles here. And these are known as Bragg peaks, and they tell you what the periodicity of the film structure is. So this film has permalloy, which is a magnetic material, separated by 5 angstroms of ruthenium, and then that's done n times. So N4, 8, and 16. When it's only 4, then you have a thinner film. When you have 16, you have a much thicker film. You see how closely spaced the thickness oscillations are, because we're in reciprocal space. Thicker films give more oscillations. And we can do things like use this technique to measure process-dependent magnetic properties. You can see that the red curve here represents a 5-minute wait between depositions, and you can see that the thickness oscillations die out here, which means the film is becoming rougher. And that has distinctly different magnetic properties. Here, the magnetic moment versus magnetic field is plotted, and the rough and smooth films and a contaminated film, there's a comparison here of them. And you can see that you're developing, for the contaminated film, there's a small opening of the loop in the middle. And this is bad for devices that have a high frequency, because a hysteresis represents an energy loss mechanism. Oh, I did this just for kicks once. See how extreme you can go. And these here is changing the thickness of the permalloy for an 8-period oscillation, 8-period superlattice. And here the Bragg oscillations are more pronounced than the thickness oscillations when you go to thicker and thicker layers of permalloy. So those were exercises in X-ray diffraction, because X-ray reflectivity, because back in 2000 they developed this spallation neutron source, and here they have not an X-ray reflectometer, which is what this is. This has a neutron reflectometer. And remember, the neutrons are magnetic. So we can look at the directions of these arrows here, the magnetic arrows in the superlattice with the neutrons. In this case, we had cobalt platinum as a ferromagnet and iron platinum as an antiferromagnet. And when the neutrons have spin, they are either magnetized up or down. And you can see there's two channels here. Red is up electrons and blue is down electrons. There's a splitting here, the spin splitting, or the angle splitting between those two neutron reflectivities tells you what the net magnetization of the sample is. The location of these peaks then tells you the periodicity of the superlattice. So we have both chemical and magnetic modulations in the reflectivity curves. We tried to model this with a ferromagnet there and an antiferromagnet there, and it didn't work out. It turned out that this iron platinum 3 had both an antiferromagnet and a ferromagnetic signal. So we got this idea. Next, what if you just made iron platinum 3 film and changed the growth temperature as a function of film thickness? So deposit iron platinum 3 at high temperature. High temperature is better ordered, you get an antiferromagnet. Low temperature, it's less ordered, it's ferromagnetic. And you just repeat that process as you're depositing. Heat the sample up, cool it down, heat it up, cool it down. Do that n times and make a superlattice of ferromagnet and antiferromagnet that has the same chemical structure throughout it. And this is the example. This is iron 25, platinum 75, deposited at 600 C, followed by, that's 30 nanometers of that, followed by 10 nanometers of that, deposited at a lower temperature. So this part is ferromagnet, that part is antiferromagnet, and yes, indeed, we do see a Bragg peak there. But again, the signal to imagination ratio, not so good. And here's the reason why you see it. One Bohr magneton, which is equal to the spin of the atom, You multiply the magnetization by the magnetic scattering length per Bohr magneton. So this is a Bohr magneton, that's the magnetic scattering length. You multiply that by the magnetization, and you get 1,000 EMU per cc, which is a unit of volume magnetization, is equal to 2.9 times 10 to the minus 6 inverse angstrom scattering length. So, and that contributes to the index of refraction through this scattering length density here. So the scattering length density is equal to the scattering length density due to the nucleus of the atom. That's the chemical part. And then there's a magnetic part, and there's a cosine angle there, theta. This is the angle between the scattering vector and the magnetization vector. So it can either be positive or negative, depending on whether the magnetization is up or down. And that's what gives you a splitting of the red neutrons versus the blue neutrons here. And this tells you what the magnetization of our sample is. It's 136 EMU per cc. And that showed the hint of a Bragg peak there. We repeated these experiments at another facility and found that it's more clearly seen here. And well, that's the wrong paper there. That's published in Physical Review B. Ederlot and Joachim Fensky were the guys that measured the sample here. Oh, no, it's Thomas Serbeck. This was Thomas Serbeck's dissertation work. And this paper, this data is published in the Journal of Applied Physics. Now, let's go back to this other sample, though. Iron, permalloy, and iridium, and you get this orientation. By the way, this is how the giant magnetoresistance effect was discovered. If you measure the resistance of this material, you have spin-dependent scattering at the interfaces, and if the adjacent layers, the spins are in opposite directions, you get a high resistance state. If all the magnetization vectors point in the same direction, you get a low resistance state. So the resistance with zero applied field is much higher than the resistance at a saturation field, which can be larger than, which can be of the order of Teslas at low temperatures. So this, the origin of the giant magnetoresistance effect, is layer-dependent, spin-dependent scattering at interfaces where the magnetization vectors can change relative to one another. That's the 2007 Nobel Prize in Physics. Okay, so there we go. So there's that sample. We did a different experiment here. We're measuring neutron reflectivity as a function of angle. This in one direction and time in the other. This is a time of flight experiment. You can deconvolve this and make a reflectivity curve out of it. And at the end of the day, though, we found that if we had a model where the spins are arranged symmetrically, left and right through the layer, so they had the same angles with respect to the field, it didn't work. It didn't fit the data. What we have is the spins in the layers at the top and the bottom point along the direction of the applied field, and there's a gradual change in the spin angle throughout the layers. So this, you can't tell. You cannot extract this from a transport measurement alone. You have to have the neutrons and the modeling in order to determine that you have this fanning of the spin vectors within the layers. Oh, we're a little bit over. So again, we measured these dysprosium and yttrium superlattices, and we can see here that in the off-specular scattering, this represents the domain size. In the lateral direction, for nearly identical samples, we got weak scattering for one case and strong for another. And this is somewhat related to the other measurement where we tried to measure the inelastically scattered, or the spin wave excitations in these materials. It turns out that very small changes in the processing conditions results in a big change in the magnetic properties of the samples. And I said that we stacked 20 or so samples together. So look, 07, 18, 10A and B. These are two samples made on the same day in the same apparatus and with the same essential parameters, 45, 29 times 40, and they have different properties. So this is a refinement that needs to be done in the future in order to make these samples more consistent over the time. And here you get helical magnetic structures where this little balls have one bright end and one dark end, and the spins rotate as you go through the layers. That's what you can see. There's a little cartoon where the spins rotate one way or the other way. Oh, and this tells you, what does it tell you? It tells you what the, if it's very bright, the domains all have the same chirality and they're large. If it's not so bright, then you have left chirality and right chirality domains, and that affects the off-specular scattering. So they have to be, we have to develop a process where we can control the chirality of the magnetization vectors as you go through the film there. I promise you electrons. I'm going to show you some electrons at the end, okay? Here we use electrons to make magnetic nanostructures. These are about 100 nanometers, 200 by 200 squares. Well, that there is a hexagon. There's a diamond, another kind of diamond, a circle, and a couple of ellipses. You can make these out of your magnetic material of choice and study their magnetic properties using this device, which is called a SEMPA. Some of those samples measured with SEMPA, scanning electron microscope with polarization analysis. And here you can see that they don't magnetize in the Y direction, they magnetize in the X direction, and they're dark elements, which means they're magnetized to the right, and the bright elements are magnetized to the left. So you can determine which direction those elements are magnetized and whether or not they have a component in the Y direction or the other. We submitted a patent application for a special shape there to be used in devices, but it wasn't considered to be unique enough. So let's get to the thanks. These are all the guys that helped me over the years making these measurements here. Roy Willis, Franz Himsel, Jim Tobin, Rich Kurtz, Bill Doyle, Bill Butler, Takao Suzuki, Mark Keefe, Kamaru Krishnamurthy, that's Lee Robertson, Jamie, Jason, John, Kathy, Katie, some of my students, that's Ezil and Gian, Mike, Prakash. Oh, who is that? Those are 3 undergraduates. Here's what you get when you get your PhD. You get bunny ears behind you. That's Swatch Ali, Stefan Mott, Zihong Liu, and so on. So the last slide, I have some news for you all. After 34 years, I'm going to retire on June 1. So this is my last talk.
Hello.
I started this up in 1988 with this paper here about iron on copper. And that's my Google Scholar page. So I'm going to quote Feynman at the end here, since he was mentioned before. So I have just one wish for you. Good luck to be somewhere where you are free to maintain the kind of integrity I have described. You'll have to read his book. And where you do not feel forced by a need to maintain your position in the organization or financial support or so on to lose your integrity. May you have that freedom. And I'd like to think that I lived my entire career based on this statement here, that I was free to work on whatever I wanted to, and I maintained a high degree of integrity throughout. Some of the data I showed you was not published, but most of it is. And this is my Google Scholar page. Yeah, I encourage you to look this up. So what do you think? Anybody have any questions?
Thank you, Professor Gary. Anybody has a questions from anyone, online or offline?
So hi Gary.
Any questions from participants from online?
Hello, Professor Gary.
Yes.
Yeah. So I have one question. Like you mentioned, like first of all, I would like to thank for your nice presentation. I also wish you very good luck for your retirement, and then have a great life after your retirement. Okay. My second thing is that when you mentioned about the thick film, you mentioned there will be many oscillations in the neutron diffraction, neutron reflectivity.
Yes.
Why is it so? Is it because of the so many reflections from the lattice plane, or some other reason exists for that?
Well, it's a reciprocal space.
Mm-hmm.
So thin film means there's a large spacing between fringes. Thick film, there's a small spacing between the fringes. By fringes, I mean the spacing between the maxima in the diagram there.
Mm-hmm.
So here you can see the fringe is, where are we going? There we go. A fringe is the spacing between from one maximum to the next. So this is a thinner film. It has a large spacing. Thicker film, smaller spacing, thicker yet. So this is the basic principle of reciprocal space. Whenever you make something smaller in real space, it gets larger in reciprocal space. So, so that's the idea.
Okay.
And that's why this is good for measuring nanostructures. You make a smaller structure, and then the spacing between the resolution becomes better when you make something smaller. So that's why we use diffraction so frequently in nano techniques.
Okay. Thank you.
Thank you, Dr. Suryanarayana, for asking question. Anybody from physically? Anybody is here? Questions? Anybody from online? Professor Gary, I have a quick question related to the spin wave. You have mentioned spin wave in novel superlattice, elastic and inelastic collisions. Like, what is the range of magnetic field that we could apply over there to know the information, structural information? The range. How do we control the magnetic field? What is the range of magnetic field?
Well, that depends on the facility that you go to make the measurement. The neutron facilities that we have different beam lines with different ranges of wavelengths available, but the field available is part of the sample environment, which when you apply for beam time, you also specify your sample environment. I have been on proposals where we've proposed to add a 25 Tesla magnet to one of the beam lines. Of course, that was rejected. That was rejected by the National Science Foundation because of the cost. A 25 Tesla magnet costs of the order of $10 million.
Wow.
So yes,
Thank you.
a 9 Tesla magnet is 500,000, and that's what we normally have. And it's shared between many scientists. Anyone can apply for beam time, and I encourage, if you make your own samples, I encourage you to investigate where you can apply for beam time. Many of the facilities have strong they even have a nanoscience center where you can make the samples on site at Oak Ridge Labs. And there's also one at Argonne National Lab where you can go there, make your own samples, and measure them as well.
Okay. Thank you. Anybody? Any questions from anyone? So, if you don't have any questions, so let me summarize and thank you to Professor Gary. We are really excited about your presentation, Professor Gary, and you have given wonderful information regarding structural information of magnetic material with the help of electron, neutron, X-ray diffractions. You have also mentioned spin thermal emission, like we all know that neutron doesn't have any charge, but how do we extract the structural information? So you have clearly mentioned that definitely it has a high energy, so which we can use them to trace the structural information. You have also explained order parameter in ferromagnetic material, how to determine. You have explained very clearly. Thank you so much, Professor Gary. You have also explained the neutron diffraction, how to detect the anti-paramagnetism even at at different temperatures, 750 glass transition. You have also explained the experiment to know the structural information with the help of like neutron diffraction, L-magnetic neutron diffraction, which is really great to know it actually. I didn't know before that. You have also explained the properties of neutron with your experiment, which doesn't have charge, which has a spin, magnetic moment, energy. So thank you, Professor Gary, for giving all the wonderful information regarding this. And finally, you have also explained the reflectivity, and you also explained the spin wave in novel superlattice with using an elastic and inelastic scattering experiments. So on behalf of all audience, faculty member of our college, City College, students, online participants from various universities across the globe. Thank you so much, Professor Gary, for giving wonderful information for us. We are really excited. Thank you so much for giving your valuable time. It's a really hard time. I know that it's more than 1 o'clock over there. It's not easy to give the talk. Thank you so much for giving your valuable time. Good night. Thank you so much.
Thank you very much. And I forgot to mention one thing.
Sure.
They used to call the hard drive industry, which is the one that I contributed to, and my students are now working in it. They called it the extreme sport of physics, meaning that the developments occurred so fast that you had to really put a lot of extreme effort into keeping up. And that's the way things are going today. So there's plenty of opportunities there for bright young scientists like you guys in the audience to get involved in this extreme sport, but you have to learn your basic physics and in particular the quantum mechanical principles in order to contribute to this field. And
exactly.
thank you very much.
Thank you, Professor Gary. Good night.
Bye-bye.
Yes, another speaker is waiting for the, his talk. So now, sorry for, little late, Dr. J. Suryanarana, Associate Professor from IIT Hyderabad. So it's a great welcome to this international conference on smart nanomaterial, advances in smart nanomaterial. Is a special guest from IIT Hyderabad in the field of nanomagnetism as well as devices related to the spin and semiconductor. He completed his MSc Physics from University of Hyderabad in 2002. He also completed PhD from IIT Madras in 2007. He was a postdoctoral fellow at Tata Institute of Fundamental Research, Mumbai, National University of Singapore, and Catholic University of Leuven, Belgium. His current research focuses on understanding of the physics behind the various nanoscopic and mesoscopic magnetic material. He published more than 50 international journals, which is really great. Thank you so much. And he delivered many seminars in India and abroad. He is a visiting scientist at Karlu Institute of Technology, Germany, through IIT DAD faculty exchange program, which is really prestigious. He is a reviewer for many international journals. He graduated total 5 PhD students from his lab, and there are 6 students who are currently working with him. He received many awards, such as IEEE Senior Member, DAD Fellow, DST Young Scientist Award, etc. Today, he will share about memory storage devices for neuromorphic computing, which is going to be very exciting to see his talk. With that, I ask you that you can give your full attention, all of you can give your full attention to Dr. Jamalamarka Suryanarana presentation. The rights and privileges are given to Dr. Suryanarana, and over to you.
Okay. So thank you very much, Dr. Parvatalu, for your nice introduction. So let me just share my screen. So is it visible?
Yes, Surya.
Okay, fine. So good afternoon to everyone. I understand that this is the lunch time, but however, I'll try to finish as quickly as possible without boring you. I hope that this topic will not be boring you. Today I'm going to speak on the memory storage devices for neuromorphic computing. So as you could see here, this is a brain image, and the connections that exist between various neurons. I mean, like we can call them as synapses. So we try to develop some artificial synapses in our laboratory and try to understand the behavior of these synaptic devices, and we also try to see how they function with respect to the brain functionality. These are some of the aspects which I would like to discuss. For this, we have chosen an important material which we can call as a graphene oxide. The graphene oxide is the one which we use to prepare the synaptic memory storage devices. So before I go, just 1 minute, yeah. So before I go to my talk, this is one of the picture which reminds me, so we both are friends, myself and Parvatalu at University of Hyderabad, and it was a very old photo. When I was going through, I could find this photo. I just wanted to share to all of you. So our laboratory is Magnetic Materials and Device Physics Laboratory. Like we basically work on fundamental magnetic properties, magnetic thin films, magnetostrictive sensors, non-volatile memory devices, then ultrasonic transducers, biosensors. I can classify my work as metal spintronics, mesoscopic physics, and magnetic materials for energy and devices. These are some of my students who have been working extensively, and they are putting a lot of work, a lot of hard work to get very good data from our laboratory. So we basically work on the quantum phenomena, the quantum transport using the mechanically controlled break junction devices, the devices for the cognitive research, the memoristic devices for sensors and the neuromorphic computing. Then we also work on the spintronics or the nanotechnology. So we basically develop the magnetic multi-layers and nanoparticles. And we also try to see the magnetic effects and the solar cell efficiencies and such kind of things. Some of, I think someone has to mute. Yeah. So some of the excitements and some of the important works that we have carried out in our laboratory, the one important work that we have carried out is basically the quantum transport. The quantum transport using the magnetostrictive nano contacts. We try to make the magnetostrictive nano contacts. And as you know that the specific property of the magnetic material is magnetostriction, which means that when you apply the magnetic field, the dimension of the material will change. So what we have done is that at the atomic scale, when we try to apply magnetic field, we try to tune the gap between the electrodes of the order of 5 nanometers, 2 nanometers, 3 nanometers, so that we could able to switch the conductance between the low and high. So which essentially means that suppose if these two atoms are in contact, one would see high conductance. When they are apart, one would see the low conductance. In this way, we try to develop an atomic switch based upon the magnetostriction phenomena for the nano-electromechanical system. This is one of the important work that we have carried out. As you could see here, the electrons are tunneling. If they are far apart, the electrons will tunnel through the electrodes. So another important work that we have carried out is the demagnetization field driven the charge transport in dye-sensitive solar cells. We try to use the magnetic field effects to tune the solar cell efficiency. Then we also try to develop resistive random access memory devices for the memory applications. Then we also try to develop RRAM devices for the biosensing applications. Then we also try to develop the cantilever-based magnetometry for the biosensing applications. So outline of the today's talk is initially I would like to give introduction to the neuromorphic computing. Then I would like to discuss about the current memory technologies that we have. Then future memory technologies. Then graphene oxide-based memoristic devices for the neuromorphic computing. And finally, I will end with the future plans and the conclusion. So as you could see here, this picture, the nanotechnology is the one which made it possible for us to get the smaller and smaller devices. Earlier, if we have to store the information of 1 megabyte, we used to use a memory chip of a big room size. But as the nanotechnology has grown, we could able to store 1 gigabit of information in very small chip. The pen drive that we have right now, it can store the information of 1 terabyte. Okay. So in continuation with that, we would also have more and more memory devices like magnetic random access memory and then racetrack memory, which are under research. Like once this comes, the more amount of information can be stored in the magnetic chips. Now, in continuation with that, like as you know that in today's world, we talk about artificial intelligence and the information processing. So basically, the artificial intelligence and information processing, it requires a hardware. That hardware must be able to operate it at very low powers, and it must be able to handle the huge data. Then it must be able to operate with very high speeds and with very higher efficiencies. So now, if you look at the traditional computers, they work based upon the von Neumann architecture. So which means that if you look at our CPU, we have the computing units are separated with the memory units. For instance, if we take the RAM that exists in the computer, it will not it will not be there at the same place where we have our hard disk. Okay, so during this process, what happens is that the logical operations will happen at one place, and then the memory will happen at another place. So if you want to retrieve the data between the RAM and hard disk, you need to apply a lot of power to the device so that the energy dissipation will be more and more in the one Neumann architecture. This is one of the disadvantage of one Neumann architecture. Instead, if you have a memory device which can store the information as well as if it can also do the logical operation, that will be more advantageous for the technology. Okay, so this is one of the aim which is there in our mind. We carried forward based on this idea and try to develop RM devices for this kind of application. On top of that, in the present computer hardware, we use the CMOS technology. So where some of the challenges of the CMOS technologies are the implementation of the complicated computation and the energy dissipation during its operation. So as a result of this fact, the computing methodologies must change from the computer-centric to data-driven paradigm. Okay, so the neuromorphic computing, which is basically the brain-inspired computing, So it can be alternative for the one Neumann architecture. So some of the advantages of this neuromorphic computing are like it can do the in-memory computing, massive parallelism, error-tolerant computing, and the low energy information can be obtained from the neuromorphic computing. So the computing device that is being developed, it works similar to the brain. Okay, as you could see here, if you see a brain, it will have the logical operations and the memory at the same place. Like you don't have to go to other place to get the logical operations, and you don't have to place other place to store the information. So both will be done in the brain itself. Okay, in the same way, we wanted to develop a memory device which can store the information and which can also do the logical operation. Okay, now if you look at the human brain and computers, in the human brain there will be a parallel architecture. So here, in case of the computers that we are using right now, it consists of the one Neumann architecture which I have mentioned. The logical and the storing information will be done at different places. Whereas in human brain, it will do parallelly the logical operations as well as the storing of the information will be done at the same place. And the number of neurons that exist in human brain are 10 power 11. In computers, we have 10 power 4 neurons, and the two neurons will be connected. And by synapses. Okay, we basically would have 10 power 15 synapses in the human brain, and in computers we'll have 10 power 10 synapses. It works basically on the analog switching. This works on the digital switching. So the analog switching means like there will be a smooth variation for the current that we receive, whereas in computers there will be abrupt change in the voltages or currents that we receive from the computer. The power that is required to operate a human brain is of the order of 20 watts. However, in case of computers, one need to apply 40 kilowatts, which is a huge power to operate the computer. Whereas our brain will take only 20 watts power to do the entire logical operations and storing information, and the massive parallelism, all these things will be done with the 20 watts power itself. On the other hand, the human brain will have the frequency signals of the order of the 10 heads, whereas in computers we use 1 gigahertz frequency, which is a huge frequency and which can also damage the environment. Okay, so we wanted to develop a device which can mimic the human brain functionality. Like we wanted to develop a parallel architecture and then 10 power 11 neurons, analog switching, and it should be able to operate at 20 watts, and the frequencies that we use in the device is of the order of 10 heads. Okay, so 10 heads. So now the question is that how the brain can store and process the information. If you look at this picture, we have one neuron and we also have another neuron. The two neurons are connected by synapses. Okay, so due to densely connected central nervous system, the central nervous system in the brain, we would essentially have 10 power 11 neurons, and these neurons are connected by synapses. As you could see here, these are the synapses. The blue colored one is the synapse, and this is the neuron. These two neurons are connected by a synapse. Okay, so the neurons would be helpful in the information processing, and the synapses would play an important role in the learning, memory, and self-adaptability of the human brain. Okay, self-adaptability of the human brain. So now when we talk about the neuromorphic computing or the neuromorphic devices, we must know the two important parameters, which is basically the synaptic weight. The synaptic weight is defined as the connection strength between the pre-neuron and the post-neuron. So how well this pre-neuron and the post-neuron are connected, that is defined as the synaptic weight, and it is determined based upon the amount of neurotransmitter released from the neuron to synapse. On the other hand, the another important parameter we must know about the neuromorphic devices is the synaptic plasticity. So which means that the tuning or the change of the synaptic weight with the time-dependent signals due to neural actions. When we apply the time-dependent signals, the synaptic weight will change. That is how we define the synaptic plasticity. So, I mean, this synaptic weight and the synaptic plasticity properties can be tested with the memristors. Okay, so they directly store the synaptic weights. That means that when you talk about the memristor, the definition of the memristor can be defined as the change of the resistance state. Suppose if you have any device which can change its resistance state, when a resistance changes, the conductance will also change. Okay, so if the conductance changes for the applied voltage, that is called as the memristor device. And this synaptic weight and the synaptic plasticity can be tested with the memristor device. So another important parameter that one can check to show that the memristor device exhibits the neuromorphic functionalities are the long-term potentiation, long-term depression, and the spike timing dependent plasticity. So the long-term potentiation means that the synaptic weight increases with respect to the time, and the long-term depression, it is basically the synaptic weight decreases with respect to the time. And then the spike timing dependent plasticity means that if you have a synaptic device, and if you apply the presynaptic pulse and the postsynaptic pulse, as you decrease the relative timing between the presynaptic pulse and the postsynaptic pulse, if the synaptic weight enhances, that's what we call it as the spike timing dependent plasticity. These are the three important learning rules that one must take to claim that the synaptic device that you develop exhibits the neuromorphic functionality. Then you can say that your device is mimicking like a brain functionality. Now the question is, what kind of memory devices that we have and which can be used for the neuromorphic computing? If you look at the current memory technologies, we have the semiconducting memories like volatile memory and non-volatile memory. When you talk about the volatile memory, immediately after switching off the power, the information will be lost. In case of non-volatile memory, even if you switch off the power, the information will be stored within the memory. So in case of the volatile memory, we have two important memory, SRAM, the static random access memory, and DRAM, the dynamic random access memory. In case of non-volatile memory, we have the flash memory. The flash memory is the one which is being used for the pen drive purpose. So if we talk about the static random access memory, the static random access memory consists of total of the 6 transistors, and 4 are cross-coupled. These 4 are cross-coupled, and 2 transistors will be used to access and control the cell during the read and write operation. And the access time for the static random access memory is 0.3 seconds. That means that for reading as well as writing of the static random access memory takes only 0.3 nanoseconds. On the other hand, the static random access memories have been used as a cache memory, and it does not have the leakage issues, and thus we need not refresh the DRAM. We need not refresh like DRAM. We need not refresh this one because we don't have any capacitive component. On the other hand, if you look at the dynamic random access memory, the dynamic random access memory, we have a transistor and a capacitor, a transistor and a capacitor, and the capacitor stores each bit in the MOS capacitor, and thus the charged state will be treated as the 1 bit, and the discharged state will be read as the 0 bit. Okay, depending upon how you charge your capacitor, you can actually say whether you have 1 bit or the 0 bit. So it is called as a dynamic because of the continuous leakage of the current. Because you have the capacitive element in the device, there will be continuous leakage of the current in the device. That's why we call it as a dynamic. Some of the disadvantages of this dynamic random access memory is that one need to apply high power. It takes high power for the operation, and it is also the volatile in nature. Some of the advantages of the dynamic random access memory is that it is having very simple structure and can accommodate more density. It is because of the fact that we don't have many components in the device. We have only transistor and a capacitive element. That's why one can have many devices, and one can store more and more information within the dynamic random access memory. On the other hand, if you look at the flash memory, so it works based upon the floating gate MOSFET where the digital data is stored. Like for instance, if we look at the cross-sectional view of the flash memory, we have a control gate and a dielectric layer and a floating gate and tunnel oxide, conduction channel, and a substrate, source, and the drain. So the writing of the information will be done by applying a positive voltage pulse to the control gate and the negative to the substrate. What happens is that when you apply a positive voltage to the control gate, the electrons will tunnel through the dielectric barrier, and then these electrons will go and be there in the floating gate. Okay, even these electrons cannot go here or here. It is because of the fact that on both the sides we have the insulating oxide layers. Okay, the erasing of the information will be done by applying a positive voltage pulses to the substrate and the negative voltage pulses to the control gate, so that the information will be lost. So in this way, by applying a positive voltage pulse to the control gate and the negative voltage pulse to the substrate, one can write the information, and by applying a positive voltage pulse to the substrate and the negative voltage pulse to the control gate, one can erase the information. Some of the important advantages of this flash memory is that one can operate them at very high speeds, and it is also having the small in nature. The dimensionality is very small, and it also requires very low power to operate the device, and the durability will also be more. Now, if you look at the memory hierarchies in computers, we have the static random access memory, dynamic random access memory, and flash memory. So if you look at the storage density, as you go from the static random access memory and the flash to the flash memory, the storage density would enhance. And as you go from the flash memory to the static random access memory, the operational speed will increase. One has to compromise, and the best thing is basically the flash memory, so that one can store the more information in the flash memory. Now the question is, what a high-ending computing and the future memory technology demands. Like, of course, one need to store more and more information, like terabytes, 10 terabytes, 100 terabytes, 1000 terabytes, and so on. Like, the kind of technologies that are being developed are based upon the artificial intelligence and the machine learning techniques, which requires a lot of information processing. And we also need to treat so much of data from these applications. So as a result of this fact, we need to have a device which can store more information. And as we know that the flash memories have reached their bottleneck in scaling, and SRAM, DRAM, the flash memories are based upon the charge. And below 10 nanometers, what can happen is that due to the leakage currents of the stored charge, which may hamper the performance of the device. So we anticipate that we have stored the information, but however, due to the leakage current, the information will be lost below 10 nanometers. Okay, so such kind of problems may arise in the static random access memory, the dynamic random access memory, and the flash memory. Okay, so I mean, as a result of this fact, we require a universal memory which can do data storage and the logical operations. Okay, the data storage, please remember that the data storage and the logical operations must be performed in the same device, like not like the von Neumann architecture or the current computers that we have. The future memory technologies demand a device which can store the information in the same chip and which can also do the logical operations in the same chip. That kind of device we want. Now, what are the futuristic memories that one can develop to meet the above requirement? One of the important memory is ferroelectric random access memory, the phase change memory, the magnetic random access memory, and the resistive random access memory. So let's see a ferroelectric random access memory. The ferroelectric random access memory, the structure of FERAM is similar to that of DRAM. Over here, the active element in the ferroelectric random access memory is lead zirconium titanate. And here, in this case of FERAM, one can read the information very fast, and one can operate the device at low operational voltage and more energy efficient than the flash memory. Okay, one need not apply so much of power to operate the device. On the other hand, if you look at the phase change memory, so it works based upon whether the material is in the crystalline phase or the amorphous phase. For instance, if you take initially the material is in the amorphous phase, and when you apply high voltage pulses, what happens is that this amorphous phase will transform as the crystalline phase. So initially, the amorphous phase can be read as 0, and the crystalline phase can be read as 1. Okay. Once you apply voltage pulse to the amorphous phase material, the material would transform as a crystalline phase. So this can be read as 1. Okay. So this one is called as a reset, and when you have material in the amorphous state, we can call it as high resistance state. When you have in the crystalline phase, the device will be read as the low resistance state. So the erasing of the information will be done by melting the sample. Once you melt the sample, again you would attain the liquid phase, and again if you cool the sample, the material would go to the amorphous state. So it's basically the toggling between the amorphous state and the crystalline phase by applying the voltage pulses and by melting the sample, so that you can store the information as 1 in case of crystalline phase. You can store the information as 0 in case of amorphous state, which is basically the low resistance state and the high resistance states respectively. And we also have MRAM technology, the magnetic random access memory technology. It works based upon the magnetic tunnel junction. If you look at the blue colored one and the yellow colored one, the blue colored one is basically the magnetic tunnel junction. Magnetic tunnel junction. Here you have a ferromagnetic material and then a thin insulating oxide layer, and you also have another ferromagnetic layer. Okay, so the bottom ferromagnetic layer, it is basically a fixed layer, and the top ferromagnetic layer is a free layer. So when I say a fixed layer, it is with respect to the magnetization state of the material. The magnetization state of the material will be fixed in one direction, irrespective of whether you apply the large field or the small field. The magnetization state doesn't change. But however, in case of a free layer, the magnetization state of the layer can be flipped even with the smaller magnetic field. Okay. Now, in a short while, I would like to discuss what is the advantage of having such kind of configuration. Okay. So, for instance, if we send a current through such kind of the magnetic tunnel junction, what can happen is that the oyster fields that will be generated as a result of the fact that the current that is sent, this field is sufficient to flip the magnetization state of the free layer. Okay, so what it means is that if the magnetization state in both the fixed layer and the free layer is in one direction, the device state will be read as 0. And if they are anti-parallel configuration, if they are in an anti-parallel configuration, as you could see in the second picture, the device state will be read as 1. Okay, so depending upon the parallel alignment and the anti-parallel alignment, you can actually read the information as 0 or 1. Okay, again, this MRAM, the magnetic random access memory, it is a universal memory, and it is non-volatile in nature. That means that even if you switch off the power, the information will not be lost, and it is having high density. The more amount of information can be stored within the device with a very high speed, and the endurance is very, very high, like up to 10 years. Up to 10 years, you can have the endurances like up to 10 years. It is basically a universal memory. So the reading of the information can be done using this magnetic random access memory technology. Is that the cells are read by the sensing the resistance to determine the state, whether it is high or low, depending upon the parallel configuration or the anti-parallel configuration of the magnetization state in the free layer and the fixed layer. One can say whether the device is in the low resistance state or the high resistance state. On the other hand, the writing of the information can be done by the magnetic fields generated from the current that flows through the bit line and the word lines. Okay, so the magnetic field that is generated over here through the bit lines and the word lines is sufficient to flip the magnetization state of the free layer, that will lead to the anti-parallel configuration or the parallel configuration for the magnetization state in the free layer and the fixed layer, that will give the high resistance state as well as the low resistance state for the magnetic tunnel junctions that exist between the bit line and the word line. So now if you look at the operation, like if you measure the tunnel magnetoresistance through this magnetic tunnel junction, like if the device shows the large TMR, that means that you will have the anti-parallel configuration. If device shows the small tunnel magnetoresistance, it shows the parallel configuration. So another important memory register device that one can think of is basically the racetrack memory. So in the racetrack memory, it is a futuristic memory which is being developed at IBM by the Stuart Parkin, although he moved to Max Planck Institute recently, but still he has been contributing so much to this racetrack memory to reach 10 terabit per inch square. Okay, right now whatever information that can be stored with the available facilities is of the order of 1 terabit, and up to 10 terabits can be stored with this racetrack memory if it is successful. Okay, so now the question is, what is the operating principle of this racetrack memory? As you could see here, it is the vertical thing that I have shown. It is basically a ferromagnetic nanowire, and if you keep many vertical ferromagnetic nanowires together side by side, one can store more and more information. Okay, so the writing of the information will be done, or the writing or reading of the information will be done within the domain walls that exist in the ferromagnetic nanowire. Okay, so as you could see here, the domain walls are moving along the length of your ferromagnetic nanowire. So this will be done by sending a spin polarized current through the ferromagnetic nanowire. When you send a spin polarized current through this ferromagnetic nanowire, what happens is that the spin polarized current will apply a torque that exists in the magnetic moments in the domain wall. Okay, once the torque is applied by the spin polarized current on the magnetic moments that exist in the domain wall, there will be momentum transfer. As a result of the momentum transfer, there will be motion of the domain wall along the magnetic nanowire. Okay, so now the reading of the information will be done by the stray fields that will be generated by this magnetic domain walls or magnetic domains. Okay, as you could see here, if you take any ferromagnetic material, there will be a stray fields or the demagnetization fields. These fields are sufficient to flip the magnetization state of the free layer. As a result of this fact, as I mentioned previously, there will be parallel alignment and the anti-parallel alignment that will give the device state as 0 or 1. In this way, one can push the magnetic domain walls within the ferromagnetic nanowires, and one can also read the information. One can also write the information in the ferromagnetic nanowires. So this will again be a non-volatile memory, and it is also universal memory. It can do the logical operation. It can also do the information storage. Both can be done. So it is basically a typical the magnetic tunnel junction based memory register device. As you could see here, this is a crossbar array of magnetic tunnel junctions for high density storage. There will be many magnetic tunnel junctions. The more amount of information can be stored, and this can also work like a memory register device. So the parallel magnetization represents the low resistance state, and the anti-parallel configuration of the magnetization state represents the high resistance state. And we also have the domain wall memory register device. The domain wall memory register device, it is basically the resistance of the magnetic tunnel junction depends upon the location of the domain wall, the changing the relative area of the high resistance state. That means that suppose if the domain wall exists somewhere here, the parallel alignment of the pins will be more. That leads to the low resistance state for the device. On the other hand, if the domain wall exists in the left hand side, that means the anti-parallel component is more. That leads to high resistance state for the device. So another important memory state device that is being developed is basically the skyrmion based device. It is basically the resistance of the device depends upon the number of skyrmions under the fixed layer. Based upon that, the resistance of the device will also change. So now the question is, what are the limitations of the current memory technologies? The current memory technologies, they have the limitations in the form of the minimum dimensions that can be fabricated and the diminishing returns in the switching performance. So now the alternative technologies can be the resistive random access memory. The resistive random access memory, it is very simple, and you will have an oxide layer, and you have a top electrode and the bottom electrode. So the kind of structure that I have shown here, it is basically the vertical structure. You can also have the planar structure by depositing the top electrodes and the bottom electrodes on the plane itself. And if you apply voltage to the top electrode, side by side electrodes, that kind of structure we can call it as the planar structure. So perspectives of the resistive random access memory are basically like this. Resistive random access memory, like they can be operable at very high speeds, less than 300 picoseconds, and one can operate at low powers, 1 picojoules per operation, and then it is having very simple structure, and it is having the CMOS compatibility. Like ultimately, we need to combine this with the CMOS technology. Whatever device that we develop, it must be compatible with the CMOS technology, and the excellent stability below 10 nanometers. As we have seen that the CMOS that we have right now, it is having the leakage problem below 10 nanometers. Such kind of problems can be avoided using this resistive random access memory devices. And the endurance cycles are of the order of 10 power 12 cycles, and the retentivity can also be for years and years. That means these are the two important parameters that one would look when we try to purchase or when we try to develop a memory device. That means the endurance and the retentivity, how long and how durable the information can be stored within the device. Okay, that is very important. So this is an example of world's leading resistive random access memory technology based upon the hafnium oxide that has been developed by the Industrial Technology Research Institute, Taiwan. They were able to show the hafnium oxide based resistive random access memory, which works at very high speed, less than 300 picoseconds. They could able to operate this device at temperatures greater than 200 degrees centigrade, and high endurance also they could able to get, and the fast reading, they could able to read the information with the 7.2 nanoseconds, and the multi-level switching also they could able to operate, they could able to get. Okay, this is one of the important memory state device that has been developed as far as the resistive random access memory technologies are concerned. So if you compare different memory state devices and memory technologies that we have SRAM, DRAM, flash memory, ferroelectric random access memory, magnetic random access memory, the phase change memory, and the resistive random access memory. So if you look at the program or erasing time for RRAM, it is 5 nanoseconds by 5 nanoseconds, which is very less in comparison with other memory technologies, even be it MRAM technology or PCRAM technology or FERAM technology. One can read the information with 5 nanosecond pulses, and one can also write the information can be with 5 nanosecond pulses. And endurance is also at par with MRAM and PCRAM. Endurance is greater than 10 power 12. And the retention is also up to 10 years. That means that once you store the information within the device, up to 10 years, you can retrieve the data from the device, up to 10 years of the time scales. And the operating can be done with less than 1 volt, whereas in MRAM and PCRAM, one need to apply little more voltage to operate the device. And the application, one can store the information. That means that one can do the logical operations using the RRAM technology, and one can also store the information. Like in case of MRAM, like one can store the information, and one can also do the logical operations even with MRAM technology. Whereas with other memory technologies, it is not possible. Like if you look at FERAM or the PCRAM, It is not possible. Even with the flash memory, it is not possible. It can only store the information. It cannot do the logical operation. That is the beauty of the resistive random access memory and the MRAM technology. And if you specifically see the writing power for the RRAM based upon the hafnium oxide, people could able to write the information with 50 microwatts, and the switching time is 5 nanoseconds, and the retention is up to 10 years, and they could able to operate the device at 85 degrees centigrade, which is at par with the spin transfer torque magnetic random access memory and the phase change memory. Now, as we have seen that many advantages for the resistive random access memory, let's try to classify the resistive random access memory. Like there are two classifications for the resistive random access memory or the resistive switching. It works based upon the resistive random access memory. It works based upon the resistive switching. Over here, if you look at these are the IV characteristics of a resistive random access memory. So, for instance, to get the high resistance state and the low resistance state, if you need to apply only one polarity of the voltage, that means for the set switching as well as the reset switching. Over here, the reset, I mean that from the low resistance state to the high resistance state. Set means that from the high resistance state to the low resistance state. If you can get the set switching as well as the reset switching with the same polarity of the voltage, such kind of resistive switching can be called as the unipolar switching. That means that with one polarity of the voltage, you can attain both the set switching as well as the reset switching. On the other hand, if we have to apply two polarity of the voltage to get the set switching as well as the reset switching, such kind of device can be called as the bipolar resistive switching. Okay. So now, based upon the resistance switching, one can classify different memoristic devices that we have. If you look at the devices based upon the one-dimensional filaments and two-dimensional interface 3D bulk materials. Let's start with 3D bulk material. The examples are the phase change random access memory and the magnetic random access memory technology. If you look at the magnetic random access memory, it is basically the 3D bulk effect. I mean, like here, you don't deal with the two-dimensional things or one-dimensional conducting filaments. It is a bulk effect depending upon the magnetization state of the free layer and the fixed layer. You will define your resistance state. Okay, so this can be measured using the magnetoresistance. On the other hand, the PCRAM, as I mentioned, like it works based upon the crystallinity or the amorphous state of your material. By applying the voltage pulses, you can actually tune the crystallinity or the amorphous states of the phase change memory. Again, this is a 3D bulk effect. On the other hand, if you look at RRAM, the resistive random access memory, it works based upon the one-dimensional conducting channel. That means that, as I mentioned, the vertical structure of RRAM device, you have a top electrode, an insulating layer, and the bottom electrode. When you apply the high potential difference between the top electrode and the bottom electrode, what would happen is that because of high voltage pulses, there will be migration of the oxygen that leads to the oxygen defects. These oxygen defects will form a filaments, conducting filaments, one-dimensional conducting filaments that will give you the low resistance state for the device. If the oxygen defects, if they form one-dimensional conducting channel, that will give the low resistance state. On the other hand, if you reverse the polarity, there will be rupturing of the filament that leads to high resistance state of the device. So that, which means that depending upon the voltage polarity that you apply, you can actually change your device state from the low resistance state to the high resistance state. So now, based on these concepts, we try to develop a graphene oxide-based synaptic memoristic device for the Neuromorphic Computing. So initially, what we have taken is that we have taken a graphene material, and using the modified Hammers method, we try to develop the graphene oxide in our laboratory. We have done the basic characterizations like X-ray diffraction, then Raman spectroscopy, then FTIR, and the UV visible NIR spectrophotometer for the absorbance spectroscopy. What you could see here that from XRD, a strong characteristic peak around 10.6 degree. This corresponds to 002 of the graphene oxide. And then we also could see the D band and G band in case of the Raman spectroscopy at 1352 centimeters inverse, and also at 1587 centimeter inverse. So this experiment confirms that whatever G band and D band that exist in the material, it prevails, which means this is a graphene oxide material. So we also have seen the transmittance using the FTIR spectroscopy. We could see different functional groups from the FTIR like CO, C double bond O, COH, and COC. These are different functional groups that exist on the graphene oxide. As you could see here, if you see here graphene oxide at the edges of this benzyl groups, you would have many functional groups. These functional groups we could get using the FTIR spectroscopy. On the other hand, with the UV visible spectrophotometer, we could get the absorbance spectroscopy, absorbance of the graphene oxide. Okay, so there is a sharp absorption peak at 238 nanometers and a weak shoulder peak at 302 nanometers. Okay, so which exactly, I mean, these studies excited us that whatever material that we have prepared, it is basically the graphene oxide. To confirm whether it is a graphene oxide or not, we try to do all these measurements and finally confirm. It is not with one experiment or it is not with two experiments. We try to see all different possibilities to confirm that our material is pure and our material is a graphene oxide material. So now, using this developed graphene oxide, we made a device, the memory device. We have taken the fluorine doped tin oxide as a bottom electrode and graphene oxide as an active material, and the top electrode as a silver paste, the silver contact we have used. So as you could see here, this is a current perpendicular to the plane configuration. The vertical structure, when you apply the voltage, the current will go from the top silver electrode to the bottom active electrode. F2 is also conducting, so that the current will flow from top to bottom. And as you could see, this is SEM image of the graphene oxide. It shows a disordered structure with large amount of wrinkles on the surface, and these wrinkles are formed due to the overlapping of the few layers of graphene oxide sheets. Like we confirm that whatever graphene oxide have developed, it is not a single layer. There are many layers, and because of that, we could get this wrinkle-shaped graphene oxide. So the wrinkle-shaped sheets, I mean, these are due to the presence of many oxygen-containing functional groups on the surface and edges. Okay, these are because of the many functional groups. As you could see here from the FTIR, you could see many functional groups. And these are the kind of IV characteristics that we have obtained. Like if you could see here, the IV, like initially the device is at high resistance state. As you sweep the voltage, the current also increases, and we put a compliance limit for the current that we detect. Otherwise, the device will go to the dielectric breakdown region. So for that reason, we try to put a compliance current, and because of that, there is a saturation. In the reverse run, again, it followed the second path, and in the third path, and again, we could get the reset state. So as you could see here, to get the set switching as well as the reset switching, we had to apply two different polarities of the voltage, which essentially means that the device exhibits the bipolar resistor switching. On top of that, if you see the variation of the current, it is rather smooth. This confirms that we have analog switching in our device. Okay, analog switching in the device, which is very much crucial for the neuromorphic computing application. We also try to analyze the kind of IV characteristics that we have obtained using different models, like the trap field limited current model, and then the space charge limited conduction mechanism. So all these models essentially confirms that whatever the current characteristics that we have observed, they exactly mimics the space charge limiting conduction mechanism and the trap field current mechanism. And the kind of IV characteristics that we have obtained, we try to explain using some kind of the bonding that exists between the within the graphene oxide material. So essentially, if you look at the graphene oxide, if graphene oxide shows high conductivity, that means that you will have the sp2 bonded carbon atoms. On the other hand, the low conductance for the graphene oxide, which one can obtain using the sp3 hybridized carbon atoms. Okay, so So what could have happened is that by the application of high voltage pulses, the sp2 hybridized carbon atoms, reduced to have gone to sp3 bonded carbon atoms. Okay, on the versa versa, when you apply the positive voltage sp3 to sp2, and when you apply the negative voltage sp3 to sp2. Okay, sorry, sp2 to sp3. So the absorption and desorption of the graphene oxide functional group near Ag electrode may be responsible for the switching of the device. We also tried to do the retentivity characteristics and then the endurance characteristics. As you could see here, we tried to repeat these experiments for several number of cycles, more than 100 cycles. Like these are, you can see the number to 120 cycles, and we also tried to do up to 10,000 cycles. 10,000 cycles, we could see a stable resistive switching, stable resistance in the low resistance state and the high resistance state of the device. On the other hand, if you look at the endurance characteristics, we could see the device stability up to 400 number of cycles. 400 days, a robust stability for the device up to 400 cycles. We also try to get the multi-level resistive switching for this kind of device. So as I mentioned, like if you want to prove the device exhibits, whether it exhibits, whether it mimics the brain functionality or not, we have to, first of all, we need to see the long-term potentiation and the long-term depression, okay, by the application of the voltage pulses. So initially we applied a positive voltage pulse, and what we could see is that with the pulse number of which is having the strength of 1.2 volts, you could see an increase in the conductance, which essentially demonstrates that there is a long-term potentiation. As you keep applying the voltage pulses to the device, there is an enhancement in the conductance. Okay, this is one of the important property of our brain, the long-term potentiation. Another important thing is that when you apply the negative pulse, there is a decrease in the conductance. That means when you apply the negative pulses to the brain, there will be conductance decrease. This is called the long-term depression. Okay, so that means that the memory is lost, the conductance is lost as you apply more and more the negative pulses to the synaptic device that we have developed. So on the same basis, our brain will also work. If you apply the positive pulses to the brain, there will be conductance increases, the memory will be enhanced. And if you apply the negative pulses, like if you are negative mood, the conductance will also decrease, the memory will also be lost. And we also try to see the conductance change of graphene oxide based devices during the potentiation and the depression for different pulse amplitudes measured for 50 consecutive cycles. And we also try to see the gradual reset process by varying the V reset, which indicates the depression characteristics, and the potentiation behavior is observed for the synaptic device by varying the V reset process. So finally, like we also try to see the spike timing dependent plasticity by applying the presynaptic pulse and the postsynaptic pulse. What we could see is that initially we applied, this is the red color one is the presynaptic pulse, and the blue color one is the postsynaptic pulse. The gap between there is a time delay between the presynaptic pulse and the postsynaptic pulse by 1 millisecond. Okay, so with that configuration, we try to apply both the pulses at a time to the synaptic memoristic devices that we have developed based upon the graphene oxide. What we could see is that as the relative timing between the presynaptic pulse and the postsynaptic pulse decreases, there is an enhancement in the weight change. Okay, I mean, this essentially demonstrates that the spike timing dependent plasticity exists for our graphene oxide based devices. What we have seen is that there is a long-term potentiation, the long-term depression, and the spike timing dependent plasticity, which are basically the neuronal functionalities of our human brain. The long-term potentiation, long-term depression, and the spike timing dependent plasticity. So these are the three important the logical operations or the neuronal functionalities we have proved on the graphene oxide based memoristic devices. Okay, so with this I would like to conclude, and these are the papers which we have published. One paper we published in the Nanotechnology, and another paper we have published in the Scientific Report. Then this work also attained a lot of interest of media, like this memory device can mimic working of human brain. With this, I would like to thank you everyone, and if you have any questions, you are free to ask. Thank you very much.
Thank you, Dr. Suryanarayana. Any question from participants, online and physical mode? So I have one question, Dr. Suryanarayana. So what is the high memory device now which we have already developed? Like what is the high density that one can develop the device with using memory star devices?
See, right now,
Technology.
people are able to get 1 terabit.
1
terabit.
Okay, okay.
People are also reaching 2 terabits, 3 terabits, but as I mentioned, like as you go to lower and lower dimensions, there will be leakage current.
Okay.
Yeah.
Thank you, thank you. One more thing, you have also mentioned racetrack memory devices. What is the actually dimension of that device?
So the dimension of the device will be like, as you could see here, let me share that slide. This is the racetrack memory.
Roughly.
Yeah. So if you look at this ferromagnetic nanowire, this nanowire thickness will be of the order of 10 nanometers to 5 to 10 nanometers.
Okay.
Okay. So if you put a vertical structure, like depending upon how many number of nanowires that you keep, that will decide the dimension of the racetrack memory chip.
Okay, okay. And one more thing, same slide, I have a quick question, like, how do we control these domains? As we can see on the slide, the domain size is not, uniform. How do we control this? Yes.
Yeah. So over here, if you look at this domain size, the domain size will be based upon how much amount of magnetic field that you apply here, and then like depending upon the magnetic field that you apply to your device.
Okay.
See, first of all, you need to write information, isn't it?
Okay, okay.
Right,
Can we make it like a uniform, like size, by applying magnetic field?
It's possible. It's possible.
Okay, okay. So it is possible.
Yeah, you see, basically here it is not by the magnetic field. The magnetic field that is generated by the current.
Okay.
The moment you apply the magnetic field, the entire domain walls will be disrupted. We don't want that one to happen.
Okay.
We wanted to control the magnetic domain walls locally. That will happen only with current.
Okay, okay. Any questions from anyone? Online? Sorry, I would like to ask one more question. Sorry. As you, fabricated GO layer memory star devices, as you also mentioned that GO layer is not uniform. It's like a multi-layers, right? So how does it affect on stability and conductivity? Like, can we make it a uniform fabrication, or if you can,
It's possible by controlling the processing parameters. One need to do the detailed study on this one. Okay. Our main aim is to see the functionalities, the brain functionalities. One is long-term communication, long-term depression, and spike timing dependent plasticity. It is possible to control.
Okay. So, but does it influence on the stability or?
Yeah, of course it would. It will influence.
Yes. Okay. Thank you, Dr. Suryanarayana. Any questions from students, faculty across the India, across the many universities, online, offline? I know it's too late. It's already late. We are running out of time. But anyway, if you don't have any questions, let me, conclude the session and with the thanks to Dr. Suryanarayana. Thank you Thank you, Dr. Suryanarayana, for sharing, especially, for sharing my picture when we were at Hyderabad Central University. I felt so happy to share that, image, the picture. And you have explained very wonderfully quantum transport, remote control with the help of, the states lowering and hiring the resistance. And you also explained many devices, memory star devices. How do we, make the latest device with a high technology to improve the storage, storage and operation, etc. And you have also explained that, I really, we are completely have focused like electronic related work, as we know that it's not easy being a physics faculty. You have explained and you have very well SRAM, DRAM, how pulse changes, flash memory devices, it's really wonderful your presentation. You have explained. I'm the first actually to see such kind of memory star devices with FERAM, PCM, phase change memory,
Recording
which is amazing to see it. And you have also explained this
Recording in progress.
racetrack memory devices, and very exciting to see this domain motion by controlling the magnetic fields, and also you have also shown us the fabrication of GO related memory devices, which is really exciting to see it. The controlling conductivity, stability, how does it changes, and finally you have also explained the spike time dependent plasticity, which is really exciting. With that, on behalf of all audience, faculty members across the globe, students, faculty members from City College, thank you so much for your presentation. You have delivered, like anything. I don't have any words to describe your presentation. I personally impressed a lot about your work. Thank you so much. Would you like to share any final words with us? We are really very happy with you, part of this conference.
Okay, thank you. So hello all of you. So thanks Dr. Parvatalu for inviting me to give a lecture in this wonderful conference. In fact, like the previous lecture were also wonderful on the neutron diffraction. I think I learned a lot from that conference. And apart from that, so I'm also here at IIT Hyderabad. And then the students over there, if they have any questions or if they want any discussions related with the physics, I'm always here at Hyderabad. We can discuss more and more. And on top of that, if you want any help during in terms of research or a small project or internship, I'm also here to help you. And then you can always approach me with my email ID surya@physics.iith.ac.in.
Thank you so much. Big claps actually. We have got a wonderful opportunity to visit IIT Hyderabad. Definitely, Dr. Suryanarayana, we will be there with our team. Definitely will be there to see your facilities, to learn about your techniques over there. Thank you so much for giving this opportunity.
And I also wanted to add that for those students who are interested and motivated, so please underline these two words: interested and motivated and hard workers.
Passionate,
So
especially.
I can also offer some kind of internship during the summer. Okay. If
wow.
someone is
It's a great, with scholarship, with the grants. Definitely we have a passionate students. They want to do research till the last day of their life. So there are few students, I know that. Definitely I'll let you know. Thank you so much for your wonderful information. So the last quotation I would like to complete the session with a quotation of Einstein. I have no special talent. I have no special talent. I'm only passionate towards the research. That we have to believe. I have no special talent. We have to be passionate towards the research. That is the one quotation that I want to share it. The true sign of intelligence, the true sign of intelligence is not a knowledge, but intelligence. It's not a knowledge, but it's intelligence. So we have to have a passion, dedication, hard work. These three definitely will make you, will bring you, will top position in the world. Only best, participate. So we'll have another session. Will begin at 2 p.m. Online participants, please join exactly 2 o'clock. Thank you, all of you, online participants, as well as the students, faculty members over here. Thank you.
Thank you.
We have a break now. Everybody should be here, please. We have to make it grand success. So we got a great opportunity to visit IIT Hyderabad. He's my everything, I can say. He's the best So good afternoon to one and all. So afternoon session is going to start now with a great quotation of Einstein. Life is like a riding a bicycle. Life is like a riding a bicycle. To keep your balance, you must keep moving. You must keep moving. Life is like a riding a bicycle. To keep your balance, you must keep moving. So with that quotation, so now I request R. Saujanya Lakshmi Madam, Assistant Professor of Physics, going to introduce Dr. Nafisa Begum from Tübingen University, Germany. She's going to, so now, Madam, over to you, Madam. Thank you.
Thank you, sir. Good afternoon, everyone. I take it as a privilege to introduce Dr. Nafisa Begum, who has been an experimental physicist with 4 years of research experience in field of soft condensed matter physics after PhD. She finished her BSc Physics honors in year 2009 from University of Kalyani, West Bengal, MSc Physics 2011 in Indian Institute of Technology, Kharagpur, and PhD from 2011 to 2017 from IISc Bangalore under Professor Jaideep K. Basu in study of dynamics, thermal and rheological properties of polymer grafted nanoparticle polymer blend, for which she has received Professor Anil Kumar Memorial Medal for Best PhD Thesis. At present, she is pursuing her research work in the field of biophysics as an Alexander von Humboldt postdoctoral research fellow in the group of Professor Frank Schreiber, Institute of Applied Physics, University of Tübingen, Germany. On behalf of faculty members, students and online participants, I cordially invite Dr. Nafisa Begum to share some of her research points with us. Good afternoon, ma'am, and over to you.
Share my screen.
Yeah, yes, Nafisa. Great welcome. Yeah. Thank you.
Thanks. Good afternoon, everyone. I think am I clearly audible, and can you see my screen?
Yes, Nafisa, yes. I can see you. We can see your slides too. Okay,
good. So, good afternoon, everyone. I will share my one of my recent works, which is done on egg white samples using X-ray scattering technique. It revealed kinetics of gel network formation and their dynamics during thermal gelation of egg white. So this is the flow of my talk. First, I will introduce a gel, its structure and dynamics. Then I will come to the experimental setup that we used to study a protein system and probe their structure and dynamics simultaneously. And then in the following, I will come to the findings of this study, which is the dynamics of protein, followed by my conclusions of this talk. So, as we know, physics of gel is everywhere in our life. It's in our body, in our food, in our daily uses, everywhere. So what is gel? Gel is defined as a substantially dilute cross-linked system. When we have a phase separation process such as condensation, so it goes from a low volume fraction system to high volume fraction, if by some external or internal reason, some attractive interactions get induced inside the particle, among the particles, then it can interrupt the phase separation. And in that case, the particles can bind together, form clusters, and eventually they can cross-link to form a network like this, which produces a gel. So a gel by weight or by volume fraction looks like liquid, mostly like liquid. However, it behaves like a solid because of its this three-dimensional space-spanning network structure within which its molecules are locally trapped. That's why we use it as a solid. So what is fascinating about a gel is that the structure of a gel does not change with time. However, it's a dynamic system. Its dynamic changes, which meaning, let's say this picture where I put a laser pointer. So here you can see this is a data, small angle X-ray scattering data collected on colloidal gel at different times. For now, let's not try to understand the meaning of the curves, but we just focus on the three curves. So as we can see, we have three curves here collected at three different times, and they fall on each other. That's the important point we want to see now. So all three curves fall on each other, meaning there is no change in structure happening inside the system. That means the structure of the gel is static. However, if we measure dynamics, that is the movement of the particles inside gel, the particles could be molecules that are making the gel or clusters. So clusters of molecules that are eventually making gel. So there could be different meaning of particles based on different systems. So if we measure the dynamics in terms of movement of the particles of a system, that means the relaxation time of the system. Relaxation time is the time a particle takes to move its own diameter. So if we measure that with time, we see that it's changing with time. It's not just a constant line. And moreover, it is evolving, it is growing with time. This says the system has a dynamics which is evolving with time. So it is strange that how can a system that is structurally static can have a dynamics that too is evolving. So let's take a look at this video. As we can see, this is a network structure. And it's a simulated network structure showing typical dynamics that can occur inside a gel network. As we can see, the particles, these small things are particles, they are moving. They are not really frozen. They are moving. They can walk out of one branch and go to another branch, and then they can really walk through the branches, strands. So this is how a gel network rearranges dynamically without changing their actual structure. So that's why a gel can be dynamic, although its structure is static. So how to measure a dynamics? Let's say we have a simple system which has particles and they are dynamic like this. So how do we measure dynamics? Simply, it comes in our mind that if we can take snapshots of this system at different times, as a function of time, if we take snapshots, then we have the information about the movement of the particles. That means the dynamics, meaning that whether the system is fast, system is slow, or it is exhibiting a liquid fluid dynamic, like viscous dynamics, or something more complicated, viscoelastic dynamics, that we can find out if we get snapshots of this system over time. So similar principle is followed in this X-ray scattering technique, which is called X-ray photon correlation spectroscopy. However, this is a scattering technique. So note that those snapshots here are in reciprocal space. So they are not in real space. So we have to somehow extract the real space image. So in this technique, for this measurement, for the current study, we used a little bit of egg white filled in quartz capillary, then heated to 80 degrees for gelation. And at that temperature, we performed XPCS. So we maintained the temperature and immediately we started measurement of dynamics. So in this measurement, a coherent X-ray beam is incident on the sample. So this is representative of the sample filled in capillary, and a time series of the scattering patterns. So these are called scattering patterns. so the scattered image, are collected using area detector. That means the 2D detector. So a time series of the scattering pattern is collected. By integrating these each of these images azimuthally means just integrate over this scattering angle and average all of them, and plot as a function of Q. Here is the wave vector transfer. In the following slides, I will define what is this Q. So we get this type of intensity correlation functions. These are important for the information of structure. So it's like small angle X-ray scattering measurement. Each of these measurements are small angle X-ray scattering measurement. And this gives information about structure of the system. If we can follow this intensity profiles as a function of time, we get the evolution of the structure of a system. So this is how movie of those scattering patterns could be. This is an example. As we can see, as the system changes inside, we can see the reflection on this movie. So we did this type of measurements like a lot. So one of them I define here. So each of these measurements are like 4,000 of those scattering patterns, and each scattering pattern is recorded for 40 milliseconds. So like that here, 3 you can see. So like that we have 4,000 of them. And so here, as we can see, this is nothing but ultra fast small angle X-ray measurement, small angle X-ray scattering measurement. And we have gone to scattering angles much smaller than usual conventional SACs. That's why it is USACs, ultra small angle. And for this type of measurements, we need highly brilliant and coherent beam. For that, we use a coherent source in synchrotron radiation. So what is coherent source? Coherent source means it has a single frequency and parallel light. So the waves are parallel. A sun can be, since a sun is very far away from us, so the lights are nearly parallel. So it can be nearly coherent. It has many frequencies. We can take out only one. Then a sun light can be used as nearly coherent source. A laser is ideally coherent source, a completely coherent source, because it has only one frequency and they are completely parallel to each other. So ideal coherent source. However, light, so these lasers are having wavelengths which are very high, so 300 to 700, which is really high compared to seeing systems in molecular level or even smaller or nearby, because those are in nanometer scale around. So we need a source that is coherent but also tunable wavelength. So that we can get from synchrotron. In synchrotron, the wavelengths can go up to angstrom, and the brilliance, the intensity is 1,000,000 times higher than the sun. So we have tunable wavelength and highly brilliant source. So that's why we use synchrotron radiation for our study. So I will briefly introduce a synchrotron. What is a synchrotron radiation? So in this is a schematic of a synchrotron. Synchrotron. In this, an electron gun produces electrons via thermionic process, and then these electrons are they go through this linear accelerator, linear accelerator first. In this linear accelerator, they get highly accelerated and collimated. And after that, they are directed to this booster ring where they get circularly accelerated. The important, very fascinating fact here is that the speed of the electrons in this booster ring is 99% of speed of the light. So it's that high speed electron beam. and then after that they enter this this ring, which is called storage ring, where the radiation is actually produced. As we can see, the storage ring has something like this. Actually, they are not really circular, but they are bent using these bending magnets. So when the electron enters this magnet, they sharply bend their directions. So at each of these sharp bends, the electron produces the radiation. It's something like this thing, this picture. As we can see, this circulating weight ball is releasing water as it is rotating. So it's similar in this case. The electrons, when they bend, they are also releasing water at their bends. So this is how the radiation is produced, and then they are sent to this as these branches. You can see these are called beam lines. So there are a lot of beam lines in one synchrotron, and in each beam line they have their own setup. This is one typical example of the setup. So in one beam line, the beam is defined using various slits and mirrors, and then the radiation X-ray is incident on the sample, and then the scattered image is collected using a detector, which could be very close here to the sample or far from the detector, depending on the system that we are going to measure. So this is a picture of a synchrotron beam line. So now, using those setup, we could capture a video of the system in reciprocal space. So now we have this movie in reciprocal space. So we need a little bit of calculation mathematics to obtain information about dynamics, because it is not in real space. So for that, we take these images. So let's say this is the direct beam entered. So in at the center of the detector, it's the scattering angle is 0. As we go away from the center, the scattering angle increases. So this scattering angle is also defined by this wave vector transfer Q, which is here defined here. Q equal to 4 pi by lambda sine theta. Theta is the scattering angle. Actually, 2 theta is the scattering angle, so it's like 2 theta by 2, and lambda is the wavelength of the radiation that we are using. Let's say we have an X-ray with wavelength 1 angstrom or 1.54 angstrom, something. So that can be tuned. At home, we do not have too much facility to tune the this radiation frequency, but in synchrotron we can tune this. So as depending on the sample, if we require such frequency, the beamline scientists help us to obtain that. So now we have this image. We select these different Q ranges, regimes. Let's say this first one, this first ring I select, or the second ring, like this. I can select various rings of Q, and within those Q, we can see there are these pixels. It's just like a camera image. So we have a lot of pixels here. So each pixel, if you plot, will typically just look like noisy like this. So it's just fluctuates like this. So it's just a noise. So from this, we do not get yet any idea how the dynamics is. So to extract the information about dynamics, we calculate this function called intensity autocorrelation function, which will nicely look like this. If the system is a Brownian, has a Brownian dynamics, just let's say a colloidal system without any additional interactions and all, just Brownian dynamics, then it will typically look like this, just an exponential decay function, and it can be modeled using this equation, exponential decay function. This is called Sigurd relation. So here this tau is a time where the correlation G2 decays to 1 by E of its initial value. So this is defined as a characteristic relaxation time of the system. So this is a way to define the time that characterizes the system. And then this alpha says the nature of the system. So for a Brownian system, this alpha should be 1. It's just a pure exponential decay function. However, for complex systems, it could be less than 1, and then the curve, the correlation curve will look like this, stressed, or it could be more than 1. The correlation curve will look like this. So these facts, all these parameters we can extract if we just collected the movie that we saw in the previous slides. However, if our system is having dynamics, that also evolves with time, like what we saw in gel. It has a dynamics, and it's not constant. The dynamics is also changing. So for that, we need to measure dynamics over time. So let's say we measure the dynamics at a very short period of time, and then after some time again, So this type of measurement, it's like doing this task just out of the previous experiment itself. The same thing we are doing, just doing a different calculation. So this is called two-time correlation function calculation. In this, we get a correlation map. So I will explain here. So in this correlation map, the diagonal line is the measurement time, and each of these perpendicular lines are the correlation functions that we were talking in the previous slides. So now, by doing this small calculation, just a small change in the calculation, we get correlation functions like all these all these lines as a function of measurement time. This way we can get the information about how the system dynamics is changing. Then we can just model all those G2 with this equation and find out the parameters that we want. If a system is equilibrium, the system has dynamics which is not changing with time, then it will typically look like this, which gives an average correlation function, and then we know average parameters related to this system. Using this described technique, we studied the gelation of egg white. So this picture is familiar to all of us. In this process, water-soluble egg white, transparent egg white, transforms into gradually white insoluble gel. So here, the native proteins in egg white unfolds, denaturates, and cross-link to form continuous gel network structure like this. So how did this happen from here to here? So this kinetic we wanted to know. So to find out this kinetics of gel network formation, we just saw this intensity profiles as a function of this Q, which Q I defined just now, and then so using this intensity profile, simply by looking at the intensity, how it is changing over time, we can see how the structure is evolving. So as we can see, this is a simulation picture which shows how the network can grow. And here we can see our experimental data, which also shows that the growth of the network is quite rapid, like what we see here. So, and they are so rapid that they are exponential. They can be described by an exponential function. Importantly, we can see that the network growth is almost finished here. And then it's almost flat, which means by 200 seconds at 80 degrees, the growth of the gel network in an egg, in egg white, is almost done in 200 seconds. it will vary when we heat at lower temperature or at higher temperature. Now we could also find out that how big are these network mesh is something like this. So the size within this, which if we plot, so there is some further calculation I did. After that, I plot here the network mesh size as a function of measurement time, which I could see that is around 400 to 500 nanometer. So around this wavelength, let's see how the dynamics is from those correlation function map. In the initial stage, we actually do not see, we can't say anything. It's like just a noise. And then we say that, okay, we do not observe any dynamics. And then a very narrow line appears. Narrow line means the system is very fast. It has relaxation time, which is very small. So that's why there is a very narrow bright line. And then as the bright line widens, means the system is getting slower. So its relaxation time, which is actually given by this width of this bright thing, is getting higher. And then there is no growth. So the dynamics stabilizes. We could extract the correlation functions from these maps like this. They're presented here in this figure. And then we could model them using the relaxation time, the Sigurd relation, which we discussed in the previous slides. And so here, just to remind again that we have the correlation function like this. We model with the Sigurd relation and to find relaxation time. Tau is the time, this is the time, and alpha is like whether it's exponential or it's more than exponential or it's less than exponential. So these two parameters only we will focus on. So the first one, the relaxation time, as we can see here, so grows with time. So as you can see, it grows with time. This is also an exponential growth. And then after that, the dynamic stabilizes. However, it shows some kind of fluctuation. So some additional periodic fluctuation it has. Not really fluctuation, additional periodic, periodic fluctuation, not just noise. That is an indication of dynamic heterogeneity. It's called dynamic heterogeneity. And if we see the length scale dependence of the dynamics, we see it's kind of relaxation time as a function of Q varies as Q to the power -1. It's a signature of ballistic dynamics. It's not Brownian dynamics. If it has to be a Brownian dynamics, it has to follow tau proportional to Q to the power -2. But here it's -1. So that is often told as ballistic dynamics. Ballistic dynamics is something like a dynamic, like we are throwing a ball. So it's not a neutral collision happens among the particles which is called a Brownian motion, which is having a Brownian motion. Here it's like much more ballistic. Now if we see how alpha goes with this, we can see alpha was 1 initially, around 1. This is like, initially it's like Brownian, but later no, it goes very high, and then it's called compressed. It goes so high. Alpha higher than 1 is called compressed exponential relaxation dynamics. This could happen. The literature suggests that this could happen due to this sudden rapid network formation. During a rapid network formation, there could be a lot of stresses that generate in the system and get trapped. They're trapped. They can't get the power to release. When later the system gets time, it slowly releases those stresses. So, and then can give rise to such dynamics. For example, here, this is one stress It's one stress in a simulated network, and release of such stress can give rise to the movement of all these area. So one stress releases breaks, let's say bond breaking, and then it can lead to a lot of movement around this stress. So this is a video, as we can see how they release. So these bonds are breaking, these bonds. So this is how they can release the stresses. And such relaxation of those trapped stresses could give rise to this alpha much higher than 1. That is this compressed exponential relaxation dynamics. Also, this temporal fluctuation we saw in the dynamics. With this, I'm already at my conclusion, saying that we demonstrated an experimental setup which is capable of measuring structure and dynamics simultaneously. And we use this to study a real protein system, which is egg white. And we found that the egg white, when we heat at 80 degrees, they initially showed no dynamics, where during which the actual structural network formation happens. But after the network formation, the dynamics starts evolving, they grow, and then they stabilize after certain times, during which it again has this structural reorganization without changing the overall structure inside the system. With this, I would like to acknowledge my PhD supervisor, my postdoctoral research mentor, my collaborators before and now, and then my master thesis supervisor, my facility groups of DAISY, ESRF, Photon Factory, and my funding bodies, AVH and DFE. With this, I'd like to thank you very much for your attention. Please let me know if you have questions. I would be happy to discuss.
Thank you, Nafisa, Dr. Nafisa, for your presentation. Please, questions from online and as well as physical. Yes, please.
Yeah. I will stop share because I can't see. Yeah. I can't hear the question.
Yeah, Nafisa, thanks for your presentation. It's a really nice one. So one question from my side. So how can you maintain the sample temperature at 80 degrees centigrade while taking the XPCS data?
Yes, so we have a temperature control stage that we had to actually mount. So we had to do this design. We made the setup at home, the stage, and then we took that to the beamline. We removed the stage they have and mounted our setup, our stage, so that we could maintain our sample temperature. And then it maintains the temperature what we want. It can maintain up to the precision of 0.1 degree centigrade, up to the accuracy of 0.1 degree. So using it is the company name is Linkum. So they may design this type of setup.
Oh, great. Yeah, the same topic. Can we maintain that temperature like more time, like 40 minutes, 1 hour, like that? Can we keep it?
Yes. As long as we want, even, yeah.
Yeah, okay. I have a same kind of similar question. Like, did you optimize the 80 degree temperature for that gelation? Like, did you test various eggs, optimize the temperature 80 degrees for everything, all eggs?
No, we took this information from literature that at 80 degrees, so egg has more than 100 types of proteins inside, and they have different gelation temperature.
Okay.
So at 80 degrees, most of them, like except one component, possibly, most of them are denaturated. So
Oh,
we
great.
chose that temperature. Yeah.
Oh, very nice, very nice. Thank you, thank you. Any questions from online? Okay, if you don't have a questions, can I? Yeah, So let us, thank you to Dr. Nafisa Begum from Germany. Yeah, Dr. Nafisa, you have given a wonderful presentation on topic gelation of eggs with the help of X-ray scattering, and I was so excited about this presentation, this work, and it seems like a simple problem, but you explore like everything from that.
Yeah.
And you have given a wonderful information. Structure is remains same, dynamics is changing. I have a question related to this. How do you simulate this dynamic? Sorry to ask the question. How do you simulate this dynamics?
Okay, so yeah, the people like I don't do, but I have a little bit idea. Like I have gone through a little bit
Okay.
about it also. So my colleagues and others do simulate. They can simulate a network structure based on like it depends. We can take particles and introduce attraction between them, and then we lead them to form a gel network, and then we study the dynamics in a simulation way. So
What
it
do you
is
have used
possible.
to do the simulation? What software? What is the?
But many people can do just using MATLAB or
Okay.
LAMPS using post-grain molecular dynamic simulation. I have friend who could do just MATLAB, but really big code because
Okay.
MATLAB
Yeah. Yes.
is not so advanced like coarse-grain LAMPS softwares and others.
Yeah.
So
I
it is
remember when we
possible
were in
to
IISc Bangalore, you guys also doing the simulation, right?
Yes,
Right.
I did some this coarse-grained molecular dynamics simulation using LAMP software. So it's
Okay.
easy, much easier there. But if we have to do it in MATLAB, then we have to define everything. We do not have any feed in like they are in LAMPs.
Okay.
So it is possible to do
Oh, great. Thank you so much.
various.
I really appreciate for that simulation and everything. And you have explained wonderful, even stress dynamics, everything, Thank you so much, Nafisa, Dr. Nafisa. And, all the best for your, future endeavors. I'm sure you're going to be one of the faculty in IISc Bangalore soon. Thank you so much for your wonderful presentation. All the best. Thank you.
Thank you. You are welcome. Okay,
Yeah.
thanks. Bye.
Yeah. With this, we'll be moving into the another speaker. Second speaker in afternoon session, Dr. Pamu, D. Pamu from IIT Guwahati. Let me. So, yeah, good afternoon to all. So now, another speaker from IIT Guwahati is also invited speaker from such a great institution, IIT Guwahati, Professor Dr. Pamu. Now I request Dr. Vasudeva Reddy sir, Assistant Professor of Physics, to introduce him. So over to you.
Thank you, sir. Good afternoon to all. Welcome to the last session, last talk of the day. Dr. Pamu, Associate Professor from IIT Guwahati. SAR is the special one for us. SAR name refers the size of the nano, but his profiles refers the surface area of the nano. SAR completed his graduation from the Silver Jubilee Degree College, Kurnool. So after that, he did his PG, PhD, postdoc, MPhil from Hyderabad Central University. Now he is working as associate professor at IIT Guwahati. So far, SAR completed 10 major research projects. One more project is ready to start. So far, 6 scholars awarded PhD under his guidance, and 11 students are pursuing PhD. Really, it's a great one. So the last one is, so far SAR has 122 publications, 122 publications. Really amazing, sir. This number shows your interest and your passion towards the research. So with these words, I hand over the session to Dr. Pamu for his presentation. Thank you.
Yeah, very good afternoon to all of you. Can you hear me?
Yes, sir. Yes, sir.
Yeah. So thank you for your nice introduction. I'm happy to be with you people this afternoon. Because my bandwidth is bit, internet connectivity, so I am just closing my video. But at any point of time, you may stop me and ask questions. I am happy to do that. So today I'll be briefly discussing about what we are doing. This is one of the areas which we deal with, but there are many other areas we look into. So microwave ceramics is my first love. So mostly whenever I go, wherever I go, first chance is given for the microwave ceramics. And we'll try to see why they are important and what is the practicality of these ceramics as we go on. So here, most of the times, as we are talking about hello, can you hear me?
Yes, yes, yes. We can hear you.
Yeah.
We can hear you. Yeah.
Yeah, thank you. So we'll continue. So in this, as we are looking at the smartness of the material, so we will see in this case why the what is the smartness that we are using, or what is the flexibility that we have with the nanotechnology, and how in this case most of the times probably you have been listening or you will be listening to the smartness of nanotechnology clearly. But here in my study, I would like to discuss the smartness of nanotechnology in microtechnology as well as in electronic applications. That's what I would like to show. So I thought of giving brief introduction to thin film technology, but I don't think time will permit us. So I'll move on to directly to the particular composition that we have chosen here. Why we have chosen this particular composition, that I will come to you little later. And this is a brief outline of the talk I am going to give you. So firstly, these materials are used as a dielectric resonators. So let me define what are the dielectric resonators and where they are used and why they are important. And these dielectric resonators are nothing but unmetallized objects. That means they should not be metals, which functions as a resonant device by means of reflections at the dielectric constant and the air interface, dielectric air interface. Why it is so, why it is important, we'll see as we move on. Why these resonators are important? Because of their excellent properties, and they are used in any communication you name, they are there, whether it is in the space or in the aircrafts, whether it is in the missiles, wherever you name, whether it is cordless phones or cellular or mobile stations, anywhere you name, these materials are required. But the good part with these materials is that you don't have to do a much of a fabrication or a much of a further processing. Once you prepare a material according to its standards, then it is ready to be used as a device. That is the flexibility we have with these devices. That's where they are very popular. On the other hand, it's not very straightforward also to prepare. And our focus here is that we will look into the preparation of these materials. How do we prepare technically so that we can achieve the properties of our choice? At the same time, we can make this material suitable for commercial or space applications. That is what is our objective here. By the way, this project is sponsored by IPR, Institute for Plasma Research, under the National Fusion Program, where these materials are required in the nuclear reactor. So this where we are trying to focus. We want to develop a material for in the nuclear reactor to be used as a microwave window. That is the purpose. That is, this project is sponsored, and we will show you some of the deliverables as well. So if we look at the dielectric resonators, these are the new ones. But what was the history? If you look at in the previous years, cavity resonators and microstrip-plane resonators are earlier they were used. But what are the problems with these cavity resonators and microstrip-plane resonators? Are that their size, bulkiness. Cavity resonators are very bulky, and they will occupy a lot of space and all. And as we are looking at the miniaturization of the device, this will not facilitate. Even the same problem with the microstrip-plane resonators. But dielectric resonators are very compactable, very compact in the sense, these tablets looks like the resonators looks like your paracetamol tablet, where the thickness of the tablet is slightly thicker compared to what you get what is your paracetamol looks like. So that's where they are very light and they are very compact and they are very effective, and compared to the cavity resonators and microstrip-plane resonators. That is where people prefer dielectric resonators. Now, if you want to use any material for resonator applications, what are the fundamental properties that are required? Can I use any material for resonator application? No, because they have to have a few important parameters. Unless these parameters are shown by exhibited by the material, will not be able to use it for microwave applications. What are those? First one is the high dielectric constant, and we are not talking about a dielectric constant at a kilohertz frequencies, but we are talking about high dielectric constant about 25 to 30 in the microwave frequency range, roughly around a X band range, something like the 8 to 10 gigahertz range. So having a very good dielectric constant at that range of frequency is not very easy. That is what we need to look at. So when we look at high dielectric constant, what we are aiming at is that, high dielectric constant means it is a smaller device size. Why? Because your epsilon r is your device size is proportional to the square root of epsilon r. What does that mean? That means that you have a larger the dielectric constant, you have the smaller the device feature. That is what is the important task that we need to remember. And then high Q, so that means it's a high quality factor. That means which shows the low loss tangent. Why this is important? In the earlier days, if you had used your mobile phone around 2000 or 90, when the mobile phones have started in India, you see that when you call somebody, you used to hear somebody else conversation because of the noise and other things. The clarity, sometimes clarity is not there. The noise signal matching, like misplacing, all that used to happen. But if you have a better quality factor, the selectivity of the frequency is very clear, then you will not have this kind of interference. And the next parameter that is important is the temperature stability, or we call it as a TOF, temperature coefficient of resonant frequency. What does it mean? All this, why I call it as a resonator here? Because when you look at very high frequencies, all the devices that functions as a resonator devices, because that is very easy to function. So that is where, suppose if I fabricate my device at a 10.8 gigahertz, But if the temperature coefficient of resonant frequency is not close to 0, then what happens? Then there will be a shift in the different your resonant frequency. If there is a shift in the resonant frequency, then the moment you send this device to space, it will not respond, because there is a shift in the resonant frequency. That's where you need to clearly look into whether that still the temperature coefficient of resonant frequency is close to 0 or not. Then only you will be able to use it for microwave applications. So if you want to use any material for microwave applications or as a resonator, these properties are essential. So that is what is the main objective or the application background that we are aiming at. And these are the, of course, when I also told you these are all required for microwave window application. Same way, the same properties are required for it is the same properties are required even for a microwave window, but microwave window needs extra thermal conductivity, which is also essential, and we are exploring in that direction as well. So now when we talk about dielectric resonators, this is not a very great concept which we don't know. This is very known, and we would have studied in our electromagnetic theory, where Lord Rayleigh showed that an infinitely long cylinder of a dielectric material can serve as a guide for electromagnetic waves at certain frequencies. So when you feed the signal at a critical angle, where theta c is equal to sine inverse of 1 by epsilon r, that means when you feed the signal at a particular angle, then when your dielectric constant is sufficiently large, then most of the your electromagnetic wave is internally reflected. So that helps to work as a resonator. Okay, so we'll move on. So when we look at the devices that are made with the dielectric resonators, these are the devices. So there is a dielectric resonator filter, dielectric resonator oscillator, dielectric resonator antenna, and radar detectors, cordless phones, GPS, multiplexers, combiners, satellite, anywhere you name, these have to be used, because anything you want to communicate with the rest of the device, you have to have a system which will wake up the rest of the system. And these resonant devices are the good ones in that matter. So they are required, and you see that these resonators are straight away used in the, so these are the bare pellets that you have prepared in your laboratory. But the property is that whatever we have discussed in the previous slide, if this material exhibits, straight away it can be used in the application. That is the best part of these materials. So that's where the preparation of these materials with the maximum density and measuring the properties at microwave frequencies are a challenge, and that is what is our study today we are looking at. Of course, you can have a dielectric resonators in different shapes depending on the need of your application. They can be fabricated in different shapes and sizes as well, because if you go higher the frequency, and you will have the smaller the device feature, so or resonator feature. That's what you will come to know. And then okay, so far we have looked at the application background. Now why we have chosen this material, why we are particularly talking about a simple composition called a magnesium oxide and titanium oxide mixed together. You prepare a magnesium titanate, which is very simple one. Why we have chosen this material is that this material is able to show high dielectric constant at the microwave frequencies, something like 8 gigahertz, and high quality factor at the microwave frequency. And then temperature coefficient of resonant frequency is about minus 50 ppm for degree centigrade. And then we will also look at, if the time permits, some thin films of this material. And these thin films of these materials are also equally promising for various optical and electronic applications. That also we will try to look into. So now these are all our objectives. But if you look at the preparation methods and the processing temperatures of this material, they are prepared at very high temperatures. So you see that most of them are prepared at 1400 degrees C. Only when you prepare at chemical reaction, you are able to, chemical methods you are able to do at 1300 degrees C. But the problem is that when you prepare these materials by chemical methods, one disadvantage is that, the yield will be very less. Sometimes, to prepare a, microwave window, we need a powder about 60-70 grams. So 60-70 grams producing by chemical method, is not an easy task. And ultimately the properties that come from these chemical methods are very inferior. That is where, when we look at, and here in some cases we see that 1275 itself, the material is being sintered. But the problem here is that you add more additives and they will deteriorate the quality factor. They may not affect much about they may not show much effect on dielectric constant, but these any impurities or any composition or any elements you are adding, they will show a significant effect on the quality factor. So that is where, we have looked at these things, and you see that the reactions you can see here, they are very difficult to process. And another thing is that we are also aiming at one more technology called LTCC. What do I mean by LTCC? This is nothing but low temperature cofied ceramics. That means these ceramics are cofied with the silver so that you will be able to build up a multi-layer ceramic capacitance. So for that, the melting point or the densification of this material must happen below the centering, below the melting point of a silver. But we can also do it with platinum and gold about 1400 degrees C. But that way we will not be able to use it for LTCC application. Firstly, secondly, that the quality factors are also not quality factors. In some cases they are good, but they are not up to the expectation when we look into the quality, TOF size. So that is where we are aiming to looking at the processing aspects of this material, so that if we can process this material at lower temperature without compromising the microwave dielectric properties, that is what is our challenge, so that it can be also used as a LTCC. That means low temperature cofied ceramics. That is the objective of our study. So now, when we talk about magnesium titanate, the main disadvantage that we are seeing is that the requirement, the sintering temperatures are very high. Firstly, secondly, that this magnesium titanate, magnesium oxide is a hygroscopic, so it always try to form a secondary phase because of that hygroscopic nature. That is what is the main problem. So it looks like a very simple preparation method by just preparing a magnesium oxide and titanium dioxide. But in reality, the phase formation is not very straightforward. So that is the main fundamental problem with this system. So how do we handle that? We will see. And then we also tried, after preparing the material, then we also made a thin films of the same material what we have prepared, and we want to check the properties of the bulk and thin films, whether these properties are remaining in the thin film also, because in the case of bulk, your pellet required about 1 gram of powder, but in the case of thin film you are hardly having a 200 nanometers of thin film. So how a 200 nanometer thin film will exhibit the same similar properties as a bulk? That is what we are going to compare towards the end of my topic talk. That's what we are going to see. So now, to do the yield, as I was telling, when you look at some other chemical methods, the yield of the powder is very small. That is where we have chosen a polyol method, which helped us to get a larger batch of the powder, so that we'll be able to do the studies at one go, so that we don't have to prepare different batches of the powder. So for that, we have followed this method, and you can look at these things are already published in our by our group. You can check for further details. And then whenever we prepare nanomaterials, because most of us, we tend to prepare powders or materials, but we don't know how to approach the preparation of the materials. In this case, this is what I want to show very systematic way of preparation of the powders and nanoparticles, and how to characterize them, how to optimize the proper temperature, so that you will be able to prepare the material at a lower temperatures. That is what is our objective here. So we have prepared the magnesium titanate particles by the substitution of in magnesium site we have doped a little bit of zirconium, and then we have prepared the powder by polyol method. Then what did we do is that these nanoparticles we have subjected to a DSC-TGA. So what DSC-TGA will give me is that it will give me to identify the crystallization temperature. So in the simplest thing, so that is what we have tried here. We see that at 547 degrees C, there is a signature which led that the material is getting crystallized at 547 degrees. And then what we have done is that now we have taken from this study, we have taken that input and calcined this material, these particles at a different calcination temperature. So we have done at 500, 550 and 600 and 650 to optimize the calcination temperature. You may say that, sir, why it is so critical to optimize the calcination temperature at low temperature, at lower temperatures, is that because if you increase your calcination temperature, your particle size will be increasing. If your particle size is increased at the calcination temperature itself, when you want to compact the material for further densification, then the grain growth is already saturated. Then you will not be able to achieve the maximum density at lower temperature. That is where we are particularly trying to optimize the minimal calcination temperature possible, so that we may have a larger bandwidth for centering temperature. That is what we have seen here. From the XRD patterns, we can understand that we almost got from 550 degrees C onwards, we have gotten a very good crystalline phase. However, to be in the safer side, we have looked at we have chosen 600 degrees C as a calcination temperature. And then we also tried to take a Raman spectra. Why we have chosen again pondering about Raman spectra here is that sometimes if there are impurity concentrations or any secondary phases are when they are at lower concentrations, XRD may not detect. But Raman spectroscopy is the sensitive tool to find out if there are any secondary phases which can be clearly figured out from the Raman spectroscopy. That is where we have done the Raman spectroscopy, and we found that we could also get a clear spectrum even from the Raman spectroscopy. So from this, we have identified the centering calcination temperature of this material. Now that we have prepared at lower temperatures, then we have looked at what is the average particle size. So here, if we look at these are the TEM images and the SAD pattern of the prepared powder. So we can see that the TEM shows, we have, as I told you, we have a fixed 600 degrees C as a calcination temperature, and then you see that the average particle size is about in between 30 to 40 nanometers. And we have also looked at the SAT pattern, and you see that the crystallinity of the sample, and we could find out the despacing, everything, and which are exactly matching to the crystal structure of a zirconium titanate. So then we moved on to the optical studies. Why we have done that is that because in the literature, these studies are not available, firstly. Secondly, we want to know, for our particular interest, how this material behaves when it is calcined, or when we play with the particle size, how the particle, the band gap varies. So we see that here, we have taken absorption spectra for 600, 650 and 550 samples. You see that the band gap is varying significantly. So you see that that is what happens here. So now the band gap values are varying between 3.66 to 3.82 electron volts. So which is a good band gap, and the material is very highly insulative. That is what we'll be able to conclude from this study. And then we moved on to the centering temperature. Now, as I told you, when we are aiming at the main purpose of this study is two applications. First one is as a dielectric resonator without compromising the microwave dielectric properties. Secondly, we want to aim this material for LTCC applications where the centering temperature of the material should be less than the melting point of a silver, about 962 degrees C. So we want to see that if we can center these materials at lower temperature, then our purpose is solved. So to do that, since we are obtaining, we have obtained very smaller particle sizes in the, as we have seen in the from the TM studies. So we thought we will try to center at a lower temperature. So we made the ceramic discs and cylindrical discs and centered at 850, 900, 950 and 1000 degrees. And also we have done the Ritwell refinement for the sample, which is centered at 950 degrees C, to make sure that to make sure that there are no secondary phases in the sample. So that's what we have done. And then we could see that we have obtained, we have done for other samples also Ritwell refinement, and we have tabulated the the values here, lattice parameters and the volume, so which are within the range, and so there which shows that there are no secondary phases. And here one important thing that we need to remember is that whenever we center magnesium titanate, one secondary phase always forms, that is MgTi2O5, which spoils the entire goodness of a microwave dielectric response. So luckily, when we prepare these samples using the polyol method, we could able to completely suppress the MgTi2O5 as a secondary phase, and we could able to get a good response, good crystal structure, and without phase pure material. That is what. And also, we could able to center at lower temperature. And you may ask the question that how did you center at lower temperatures? So to do that, we have shown you the SCM micrographs or surface morphology, and you see that this is the first one is centered at 850 degrees C, and this one centered at 900 degrees C, and this one this one centered at 950, and this one at 900 degrees C, and this one at 1000 degrees. You see that you see a uniform microstructure is observed, and they are fully compact. So which shows that our samples are densified. Then the next question that you can ask is that how come it is possible, and why I emphasize this particular material is that in our laboratory, this student is the fourth student to work on the same material, and we have tried this preparation of this material in various ways, and this method gave us the best possibility, because best possible applications and good response. That's where we are trying to highlight. So you see that we see that very good response or a very good microstructure, uniform microstructure with maximum density is obtained. And then the next question that can come is that why, you may ask me is that you have started with the nanoparticles and finally you ended up at the micron size grains. What is the funda in that? So special in that? The specialty is that when you have a smaller particle sizes, what happens is that the surface area is larger and the reactivity of the powder is very high. So the moment we start, we subject these materials to the temperature, then what happens? The nucleation takes place, because smaller the particles, higher the surface, higher the centering energy that is available. This will lead to a uniform grain growth and a densification at the lower temperature. So we have taken that the nanoparticles as an advantage to center the material in this case. But we have also tried earlier in preparing the same material with the other method, and they did not yield us this kind of good response. But only the materials prepared using the polyol method yielded us the very good centering response or a densification response, which is our requirement. So then once we confirmed our microstructure, measured these material properties at microwave frequencies using a Hucke and Coleman method. And we have for that you can look at in the literature, and we have measured the dielectric constant or the properties at 9.5 gigahertz. So you see that the relative density of the sample is higher for the material which is prepared, which is centered at about 950 degrees C. So we could achieve something like a 97.5%, which is very good density. And also you see that the uniform particle size is a optimum here, 3.34 microns, and this sample looks very grain size is larger, but you see that there is some abnormality in the sample prepared at 1000 degrees, centered at 1000 degrees. Why? Because as you increase the temperature, then the the Ostwald ripening may occur. That what is Ostwald ripening? Ostwald ripening is nothing but the larger particles grow at the expense of smaller ones. That's what you see here in this case. This particle will as you increase the temperature, this particle try to grow at the expense of these smaller ones, and these smaller ones will disappear as you increase the temperature. That is what happens. And then when we measure the microwave dielectric properties, we could able to get a high dielectric constant as a 18, which is a very good high dielectric constant. And then you see that we have corrected the porosity. That means the density is only 97.52%. Rest is the porosity. So suppose if you eliminate that porosity also, what happens is the maximum dielectric constant maybe you can obtain is about 18.68. That means we have achieved the maximum density possible. That is one thing. And in the literature, you see that 1.166 terahertz only the quality factor, or quality factor multiplied by frequency is called that is the notation generally people use for microwave resonators. So we see that here we could obtain a 175 terahertz, which is a high quality factor. In other words, it is a very low loss tangent. So you see that at 950 degrees C, in the literature we have shown that we have seen that minimum centering temperature is about 1400 degrees. But at 950 degrees C, we could able to get the maximum density, not only maximum density, but we could also get a good microwave dielectric response, which is required for a resonator. At the same time, we could able to densify the samples at lower temperature, where this material can also be used at used in a NTCC application. That's what we have done. And then we have moved on to low frequency dielectric studies. And then you may ask, because when we use these materials at microwave frequency measurements, we will not apply any silver paint or anything. Straight away we use the materials with a different aspect ratio. That means diameter to thickness about ratio should be about 2.5. That is what is the sample size. But we also want to do a low temperature, low frequency studies. We want to see in the low frequency how this material behaves. We see that at lower frequencies, the dielectric constants are very high. It is giving a very good high dielectric constant, because as you go higher and higher frequencies, the contribution to the polarization decreases further and further. You know that at lower frequencies the dielectric constants are very high, because you have a space charge polarization contributing to the dielectric constant. As you increase the frequency, then dipole polarization contributes. As you go further, electronic. So slowly these polarizations get relaxed, and ultimately you will have a very low dielectric constants at a higher frequency. That's what we can see from these studies. And the quality factor also, or loss tangent also, we have seen. And we have also tried with respect to temperature, the dielectric constant, how it is changing. With respect to dielectric constant, both dielectric constant and loss tangent both are increasing. Why? With increasing temperature, what happens? Your dipoles will be getting some thermal energy, which they will align into the field direction when you apply the temperature. But at the same time, that leads to the loss tangent as well. So here you see that inside we have done at 20 megahertz. We have measured the dielectric constant as a function of temperature, and we are able to get a very good dielectric response as well. So this is what we have done at a low frequency measurements. And then we have studied also the impedance spectroscopy. You may ask, question is that what is the point in doing an impedance spectroscopy? Because we want to know what is the contribution from the grain and grain boundary to the conductor. Or in other words, we also want to see what is the activation energy that is available to the system. One side I am saying that I have very good dielectric constant and my band gap is very high, but a similar response is remaining in the material or not. To check that, we have done the impedance spectroscopy, and you can observe this. And then we have calculated the activation energy. You see that if you look at the activation energy is very high here. So you see that the activation energy is about 3.58 electron volts at 2 megahertz. So that means, which shows that the quality of our preparation or the material is very good. That is where to find out we have done the AC conductivity studies also to find out the goodness of our material for microwave applications. And these are some of the materials that we have developed in our laboratory. These are all called different zirconium titanate dielectric resonators only, which are required for the space applications. And these samples we have sent to SAT Ahmedabad, Space Application Center Ahmedabad, and they have tested for the space applications, and they said these materials are capable for suitable for space applications. And these are all lower the frequency, higher the frequency, you will have a smaller the sample size. So these are varieties of the samples we have prepared, and these are some of the rectangular samples which are required for microwave window applications. And we have also prepared some of the materials for microwave window applications. So with this, we'll conclude with the bulk part what we have done. Now I'll move on to briefly to the thin films. Now we could achieve our targets in the bulk form. Like, we want to prepare these materials at low temperature without compromising the microwave dielectric property. And these materials should be suitable for dielectric resonator applications as well as LTCC applications. And then we want to see whether these thin films of the same material, whether they can be useful for optical and electronic applications. And to our surprise, these are all very good for that application. So what we have done is that we have prepared a sputtering target in our laboratory itself, to deposit the thin films, and study their optical and electrical dielectric properties, so that we will be able to compare the dielectric as well as the optical properties, both bulk and thin films. That is what is our idea in doing that. So these are the deposition parameters that we chose while depositing the thin films. So again, before we go into the sputtering, we have prepared the centering target, and this one we have prepared using a solid state reaction method, not a polyol method. But you see that the centering temperature in this case is as high as 1350 degrees C. But we want to check the phase purity, everything is matching, and then we have prepared the thin films by varying different oxygen and argon percentages. So what do I mean by that? Here when I say 0 OMP means here I am using a 0 oxygen mixing percentage. That means we have deposited this film under a pure argon ambience. And 25% OMP means 75% of oxygen, 25% of oxygen, 75% of argon. And 100% OMP means we have deposited the film under a pure oxygen environment. So here figure A is shows, we have deposited these films on a amorphous SiO2 substrates. Why we have chosen amorphous SiO2 substrates? Because amorphous SiO2 substrate is a transparent substrate which is required to get optical data, interference, transmittance spectra, and all the things. So that's where we have chosen one as a amorphous SiO2 substrate, and the next one is the platinum coated silicon substrate. Why platinum coated silicon substrate is we have chosen? Because we want to make a parallel plate capacitor, thin film capacitor, to measure its electrical and dielectric properties. So we need a bottom electrode. So what we do is we mask the bottom electrode to take electrical contact, and the rest of the portion we will deposit the thin film. And here we see that while playing with the different oxygen argon parameters, you see that the orientation of the plane. That means the thin films have a very good orientation in a 110 plane. Which electrical and optical properties, and that's what we have observed. We have calculated with respect to oxygen partial pressure how this orientation factor is changing. That's what we have done it here, and then we'll move on here. So what we have done is that we have done the AFM images here of films deposited on SiO2 substrate. What we have done is that initially we have deposited them at ambient temperatures. So now after annealing, we have annealed these films to induce the crystallinity. So we have annealed them at a 600 degrees. You see that this is one is a pure argon and another is a pure oxygen film we have annealed. Why we have chosen pure argon? In the case of pure argon, you see that particle sizes are larger compared to the pure oxygen films deposited. Why it is so? When you deposit the films in the presence of pure argon, the rate of deposition with argon is larger. So as a result, what happens? The nucleation is more, then you will have a large particle size. In the case of pure oxygen, what happens? The target get poisoned because of your oxygen. So as a result, your rate of deposition decreases. That leads to a smaller particle size. That's what we have done here. And then we have also done the AFM images on platinized silicon for all the compositions offered with the different oxygen percentages. And you see that this is a 100% oxygen film. And you see that all the films show a uniform microstructure with a spherical shape and a columnar growth, and which is very prominent. And why we particularly chose this one is that because your electrical applications, when you measure leakage current and dielectric loss tangent and all, this morphology is very crucial to explain the the response, dielectric and electrical response. That's where we have done the AFM images on platinized silicon. So then we have done the optical transmittance of these films, and we have seen that as deposited films and the annealed film. You see that annealed film is showing a lower transmittance compared to the as deposited film, because as deposited film is a porous film which will let the light to pass through. But whereas annealed film, the grain size is larger, so they will not let, because of that there is a lot of scattering. And we see that the transmittance is very high of these films, and then from this we have calculated the thickness and refractive index of the films. So you see that with respect to the as deposited films show very low refractive index, whereas the annealed films show a very good refractive index, because because of the porosity is eliminated. As a result, your packing density is also very higher. You see that your packing density is very poor, about 84% maximum. But in the case of annealed films, your packing density is very high. So that is where about 95, more than 95% of your packing density is higher. So you see that is where you see that porosity, how that is porosity is changing with respect to oxygen percentage. We can see here. And also we have calculated the band gap. You see that in the case of particles, we have seen the band gap is about 3.8 electron volts, which are about 30 to 40 nanometers. But the thin film, say almost similar particle size, but since the surface effect is very prominent in the case of thin films, and you see that the band gap is as high as a 4.4 electron volts. Why? What is the reason? Because most probably there is a quantum confinement effect that is coming into the picture that would have led into the maximum band gap in the films. So we have done optical constants here, and then we went to we have fabricated the thin film capacitors in order to see their response at higher frequencies as a function of frequency, and we see that you see that film deposited at a 100% oxygen is showing a better dielectric constant, because when you deposit the film at a lower temperature, lower oxygen partial pressure, probably there might be slight oxygen vacancies, that might lead to a low dielectric constant and high loss tangents. But you see here, in this case, the pure oxygen film shows us a better dielectric constant. That's what we have confirmed, and we have also tried to measure the impedance spectroscopy, and we see that we have also calculated the activation energy. Here, in this case, the activation energy is only just a 0.36 electron volts. In the case of bulk, we have seen the activation energy is as high as a 3.6 electron volts. But here you only see 0.36 electron volts. What is the difference here? In the case of bulk, the packing fraction, the density is very high, but thin films are very porous. The moment you give a little bit of temperature, the charge carriers try to move because of its porous nature. That leads to a lower activation energies in the thin films. And then what we have done is that we want to know how this impedance changing. We have done the Nyquist plots by plotting the Z double prime versus Z prime, and you see that what is the contribution from the grain and the grain boundary. So RG is nothing but a grain resistance, and RGB is nothing but a grain boundary response, and C is R indicates in the equivalent circuits the loss of the material. C indicates the storage of the material. So from this we could able to get the contribution from the grain and the grain boundary of the thin films. And then ultimately what we have done is we have also measured the microwave dielectric properties of these thin films using a split post resonator technique. This data is not shown here, but those in that case also, whatever dielectric constant we have gotten at 9.5 gigahertz, when we measure the dielectric constant using split post resonator at 10 gigahertz, we have gotten the similar dielectric constant. But in the case of thin films, the loss tangent is slightly higher because of their porous nature. So that is what I would like to say. And these films we have deposited and we studied their structure and electrical properties. And these materials are all suitable for optical, coatings and also the electronic applications. And they are also suitable for CMOS applications. Okay, with this, I'll try to conclude. These are some of the references. And we also make in our laboratory, we also make and produce as a startup different sputtering targets. If any one of you require sputtering targets, we produce them and commercially sell them. And these are some of the sputtering targets that we have developed indigenously in our laboratory. With this, I'll conclude here. Thank you all. And these are some of the facilities that we have used to prepare these samples and the thin films, and some of the characterization facilities. Thank you.
Thank you, sir. Sir, one question from my side.
Please.
Yeah, this is Vasudev Reddy, Government City College.
Yeah.
Sir, as we increase the sintering temperature, generally porosity decreases. so that volume of the unit cell also decreases.
Why?
But in your prepared sample, in all the cases, volume of the unit cell is constant. How the density increases? Density of the samples increases.
No, you
That's
are.
my question, sir.
No. When we talk about the volume, this is what we are talking about, a unit cell volume when we calculate. But when you are measuring the grain size, you are talking about a bulk density. These two are independent. Of course, one effect can be will be there on the other, but mostly the unit cell volume is dependent on the ionic radii of I am substituting the zirconium into the magnesium site. That will change the unit cell volume. But what we are seeing in the microstructure is about a bulk density. So that is the main difference.
Okay, now Ratan Kumar, please proceed. Assistant Professor Ratan, ready to ask a question, sir?
Yes, sir. Good evening, sir. It's very nice talk. Sir, I have one doubt. How does the grain shape affect the nano grain shape affects the electrical properties?
See, grain shape, that is dependent on porosity. Ultimately, how that is packing only it decides. Grain shape, ultimately grain size shape means how that shape particularly ultimately leading to the packing only matters, especially when we talk about bulk. In the case of thin film, along with the grain shape, the roughness and the strain, all these again it will influence your electrical properties. But in the case of bulk, the strain effect is very much minimized, and the grain shape will be adjusted if you properly optimize your centering temperature carefully. Then automatically the compaction is optimized. Ultimately, you will have a platelet-like structure or spherical shape, depending on how it grows. That's what I feel.
Yeah, thank you, sir.
Myself, Dr. Parvatalu, I have a question, Professor Dr. Pamu. As you mentioned, it was a really wonderful talk. Thank you. The question is related to DSC data. So how can we run the DSC, what scan rate that you have used to achieve such a high temperature scan rate? Because it takes, when you go for the,
Yeah, we have done very slow scanning actually to, sometimes what we do is we do it in a hurry manner. When you do it slow scanning, then of course, we have done very
change
slow
definitely, right? It depends on the scan rate also, right?
Yes.
Okay.
But we have done 2-3 scan rates, and ultimately we have done taken the optimized one. That is the very slowest one. Also, slow rating also did not help us. Fast rating also did not help us. Intermediate.
We have optimized 50
yes.
per minute. 50 degrees
Yes.
per minute. Okay. So thank you. One more question. How do we reduce? Like you have mentioned, reducing porosity, right? So what method you have used to reduce the porosity? Did you use the DMA technique to just press it, or is there any other technique that you have used?
No. Porosity, we have measured the density using Archimedes method.
Okay.
So the rest is the porosity. But theoretically, what I have shown you, what I shown in my slide is that porosity correction. For example, suppose if I do a spark plasma centering or a hot press, and if I can get if I can eliminate completely the porosity, what is the maximum dielectric?
Okay.
That is only the correction, because that will tell us that will tell me that how capable is my material for application.
Okay. So you have porosity. Basically, did you measure it, or just by observing the morphology of the SEM or AFM, you have mentioned this is the porosity? Did you calculate porosity by any?
No, we have not quantified. We have not quantified because when once you go above 97% of the density, the minimal things, the 3% of the porosity will not make much influence. So, but if I am below 95, then I have to quantify the porosity for especially microwave ceramics.
Okay, okay. So, okay, thank you.
Somebody was asking in the chat. Somebody was asking
Okay,
one
yeah.
more question.
Please, online participants, anybody from.
Can you explain
Unmute and
about
you can
resonant
speak.
frequency in tangent loss? Yeah, resonant frequency depends, there is an expression, based on the sample dimensions and initial dielectric constant values, we can roughly estimate the resonant frequency of the material. Once we estimate the resonant frequency, then you get a curve, sharp peak. From that, we take the full width at half maximum and try to get the quality factor. Quality factor is nothing but a 1 by tan delta. So that is what is the loss tangent that we get.
Okay.
I hope I answered Saujanya.
Sir, good afternoon, sir.
Good afternoon.
Sir, actually in my samples, whenever I have done in nickel cobalt ferrite samples, for one sample I got the tangent loss at low frequencies, and other samples I got at higher frequencies. So that's why I asked, so what will be the parameters?
No, actually you are confusing, because when you talk about ferrites, no?
Okay.
When there is a magnetic component, magnetic element is there, the microwave measurement that we do with the TE01 delta mode, and these microwave ferrites are very lossy by nature. So if you want to do microwave ferrites, these are all nickel, whatever ferrites you are saying, they are also used at microwave frequencies for different applications. In that case, you have to use a waveguide method to measure, to obtain, these properties. If you wish, you can contact us later. We will help you, if you wish to do these measurements. We can measure in X band and K band, to get a, but for that we need to prepare samples in rectangular shape, to do those measurements. Then only it will make much meaning. If you measure at low frequencies, it may not help, because these are all high frequency material.
For that samples density should be high, no, sir? It's around.
Not necessarily, because when these are all used for mostly microwave absorption and all. In that case, density we don't really consider, because ultimately in the dielectric resonator case, we want to store the electromagnetic energy. But in the case of microwave ferrites, especially absorption, we want that microwave energy to be absorbed in the material, so that my device below that is safe. So there is a different contrast of application.
Okay, sir. Thank you.
Wow. Thank you, madam. Thank you for asking question. Dr. Prama, I have one more question. What are the major challenges with this material to design for industrial applications? What are the challenges that you have been facing?
Yeah, the main challenge is that reproducibility of the material, and the humidity also is an important factor, because of the hygroscopic nature of the magnesium oxide. It always tend to form a MgTi2O5 as a secondary phase. That will drastically deteriorate the properties of the material, firstly. Secondly, densification is a challenge, and we could able to, make it and prepare samples which are suitable for space applications.
Wow, thank you so much, Dr. Pramo. You have given a wonderful presentation for today, last session. You made us to excite about this material and challenges, applications of these electronic applications of ceramic material, nano ceramic material. We are very happy to see your presentation.
Thank you.
And with this, on behalf of all audience, faculty of the Government City College, faculty of the all around the universities, and my dear students, thank you for for giving a time to us. It was a really wonderful presentation, Professor Dr. Famu. Thank you.
Thank you.
We would like to take one picture with you. Please be, video mode.
Just a second.
Video. Thank you. Thank you.
Yeah.
Thank you. After a long time, great to see you actually. Thank you so much.
Yeah, good to see you. Thank you.
Yeah. One more, one of your friend also, friend of my colleague actually, from Silver Jubilee. Mallikarjun from Silver Jubilee.
Yeah. Probably is there or?
Yeah, I think, I don't know where is working. He's at Kamam now.
Okay, okay. Yesterday he called me. Okay, then thank you so much for having me.
One picture, bro. One picture.
Yeah,
just
please.
come.
Is it done, Paratalu?
One second.
Yeah.
Thank you so much for your great presentation. So I'll talk to you soon. Thank you. Right.
Thank you. Yeah.